stream. Looks like we are live on YouTube and on Twitch and on live.diode.zone/scanlime. Good morning, everyone, or hello from the archives, whenever and wherever you're catching this. I figured this could be a pretty chill project plus hangout chat kind of stream. I'll have a little, there's sort of a little conference room server I'm experimenting with, which is the link in the top left corner, the join.scanlime.org. You can join with audio and or video if you would like, but you can also just close that dialogue and get text-only chat. I skipped a step in setting up the stream. Hi. Well, let me show you this sewing machine since it's a pretty weird piece of kit, and that's the project for today's stream. That's my knee. Still getting used to this studio. It is a good bit smaller than my previous studio. But yeah, we might have to go for the overhead view at some point, but the front view is pretty nice on this thing. Oh, now we can see that my window needs resizing. Hello, hello. Welcome to the chat. Thanks. The Mr. Radar says, I love the aesthetic of your sewing machine. Yeah, it's an interesting device. So as you can probably tell, it's pretty DIY. Something weird's going on here. This is an old project I did in like 2010. Should get my other video recorder started before I forget. Cool. I've been having trouble, among other things, with this camera overheating. This camera is recording in 4K, so it probably has a lot of processing to do. But I figured maybe I could separate my recording needs into maybe getting bursts of 4K when I especially care about it, but then also just having a continuous recording of the 1080p HDMI output. So now I've got the HDMI viewfinder output from that camera going to both the streaming machine and to a separate recording setup, which seems like it'll be much better for actually keeping all the video and audio in sync during editing. Okay, so this thing's already got oscilloscope probes dangling off of it. Let's maybe take these off for the moment. Anyway, this is going to be a bit chill. I'm going to try not to like rush into trying to be entertaining 100% of the time, but more focus on having just a pretty chill environment that people can hang out in, and also in making space to get some interesting footage for later and to answer questions and to just actually fix this sewing machine. T asks if this was a CNC sewing machine. Well, I guess it depends on what you mean by CNC, but not really. I mean, I had some pie in the sky plans, I guess, of making a CNC embroidery machine based on another modification to this. This is like covered in dust. But yeah, I didn't actually do that. What I was doing is I was making these like plushy stuffed animal critters a while ago. Not a whole bunch of them. Like, I don't know. This was like one of my short-lived hobbies a while ago. I was making just like cute plushy things, which I kind of want to go back to at some point. But I feel like the more immediate need for this sewing machine to be working is so that I can sew some face masks, because I've been just wrapping a t-shirt around my head, and that kind of sucks. So I want to fix my sewing machine and make face masks, but my sewing machine has had this annoying problem where it crashes, and that's where we're at right now. And I'll explain more about like what this even is, what's going on, and why it's crashing as we make some progress here. I took a brief look at it already before committing to this stream, and I have some pretty good ideas of what's going wrong, but I kind of want to take you through the process on video, and then we can actually try some solutions and see if that works. But yeah, it's kind of dirty. This circuit board is also pretty dusty, and it's, I'm sure, really delicate. This whole thing is extremely prototypey. Like, I never intended to build more than one of these. It was just a prototype, but also a thing that I like wanted to be able to use. So it's got this like point-to-point wired perf board back there. Yeah, the wiring is pretty much a mess. Okay, I'm just going to take the O-scope off of this for a bit and try to position the camera and get some better footage of what's going on. I had a much lower resolution camera last time I tried to film this crazy beast. It's also not using its original foot pedal. Gosh, how am I going to keep my knee out of the frame? Gosh, maybe I could do a little studio tour, because this, yeah, it's a little bit small compared to my previous one, but I'm trying to figure out how to make the most of the space. Gosh, I hope I don't knock over this camera. A sewing machine like sowing seeds, that would be interesting too. Automated farming bots. think I need new batteries. Whoa. Audio's back? That's interesting. This definitely needs new batteries, but I'm facing compounding problems now. The green screen is trying to fall over. I'm losing my... Okay, that might be it. Thanks for bearing with me. Huh. It's a noise I didn't recognize. I think this little tablet has a secret fan. Okay. Oh, yeah. I think this little tablet is working pretty hard. I didn't even know it had a fan. That's interesting. Cool. The green screen is still trying to fall over, and I bumped the light, which switched it to the wrong color. This is all wonderful. There's like nothing to attach the green screen to. I haven't really committed to any of this enough to start like making modifications to the room for studio purposes, so like if this is mostly working out, I will probably just paint some of the wall green if I end up wanting a green background even, but right now I've got this freestanding one which keeps trying to fall over because it's designed for something kind of different than what I'm using it for. And there's just, everything is really crowded over here, and I'm trying not to knock over my nice camera. Hmm. Gosh, this camera gets warm even when it's not recording in 4K. I think I'm just going to have to reposition this once I really get settled in. Sorry. Chat got stuck again. Such a common bug. So many different ways that you can get the auto scroll to stop scrolling in different apps that are written completely independently. I'm just gonna have to go get a zip tie. Oh, it's nice and cool over here by the massive fan. I've got the door closed both for noise and because I was kind of too stressed out to deal with Tuco lurking around edible wires. Zip tie. I'll zip tie the green screen to the window blinds. What could go wrong? I figure most of the blinds in this place have a very limited lifespan on account of Tuco. He's already caused significant damage to some of them. He just decides he wants through, and he'll just sort of like bat at the leaves, whatever they're called in the blinds, until the metal fatigue breaks them off. And he's done that in a bunch of places already. He's very good at destroying things when he wants to. Like, he's pretty effective at being a cat. But yeah, maybe I'll break the blinds this time in my quest to be as cat-like as possible, clearly. Okay, I probably should have done this a while ago, because Tuco's threatened to knock this over several times already. Tuco is a great cat. I should see if I can find him so I can stick the Wi-Fi camera next to him so he can watch him even if he's not actually in the room. Ugh. This light is also kind of awful. It's like a DMX LED bar that I'm using to backlight the green screen. And it works pretty well, but it takes up a lot of space for what it is. I really just should wall mount it. That's kind of in the category of things that I will do to this room once I'm more certain that I have a layout I'm happy with. Let's see if the Wi-Fi camera works. That is... Yeah, I'm going to try to carry this to where Tuco is. This camera has been kind of flaky, which, I don't know, kind of fits in with my whole mental model where nothing that's on Wi-Fi should really be trusted, but in this case it's battery problems. Is Tuco? Oh, here's Tuco. Tuco is eating. Oops. That was the automaton, not the camera. This camera also has interesting H.264 Wi-Fi glitches. Yeah, I think something I'm doing here is running like kind of over capacity. Like I don't know if that's a problem with the hardware video encoding or with the Wi-Fi connection or like CPU throttling or thermal or something, but something here is working too hard and failing in interesting ways. Glitch cat. Like the Wi-Fi itself is pretty good, but maybe there's a compatibility problem with this phone or something, or maybe I just need to switch video servers. I'm just using one of the random freeware video servers from the Play Store. Yeah. Let's switch to the computer, but with a cat overlay, maybe. Something like that. All right. So yeah, this is what the chat hangout environment looks like if you care to join that. There's text chat, and then there's a whole system for doing presentations and shared whiteboard and all that here. But I haven't so far been using that for these streams, but it's a pretty cool system. If you've been using like Zoom for meetings and you're kind of annoyed with it because of all the software that you have to give access to your data and your computer, and all of the other people that you have to trust to use the service successfully. And if any of that's annoying, then there are some open source alternatives that you might be into. Jitsi, Jitsi, is pretty popular. We use that like once or twice here. And it seems to have just a lot of simplicity and like mobile compatibility that makes it easy to use. This other one that I've been using for this is Big Blue Button, which is kind of more designed for classrooms, but has some features for like presentation sharing and moderation that seem useful for this environment. All right, so yeah, this is the project. So I blogged about this at the beginning of 2010, so it is a full decade old. How long was it between doing the project and blogging about it, even? I don't know if I even mentioned like when I specifically made it, but it was probably something I did over the past like month or two before actually writing about it. So yeah, what else was I sewing here? Oh yeah, that's the most complicated thing I ever made. I did like a cosplay, like a single unit of cosplay, and I made this Ramona Flowers purse, which like you can see a bunch of my mistakes here, but I was proud of it for what it was. But yeah, this is more like what kind of inspired me to do the modification. I was just trying to do what and I'm sure a bunch of people that are better at sewing than I am would just not even consider this. But I was just feeling really frustrated with how when I was trying to do sort of detailed machine sewing around stuff like this, it was really hard to operate the sewing machine at a low speed. If I just push the pedal a little bit, then the way it was originally set up, the pedal has basically a light dimmer circuit. It's just a sort of chopper that uses a triac like a transistor to turn the power on and off at every wave, every 120 times a second. It'll turn the power on sort of part of the way through one of the sine wave cycles of the AC power signal. So by just changing the phase of like when it turns on the motor during that sine wave, you can control how much power you give the motor. But it's really coarse for a bunch of reasons. So yeah, I went through that in this whole blog post. Let's see, maybe I will actually take a quick break to get some water, and then I will go through this in a little bit more detail. But yeah, the thing that I was trying to explain here is that I was trying to do some like weird stuff like fabric RFID tags and those plushies, and I was annoyed by the way it sort of stalls and doesn't work very well at low torque. And so then I went through this whole thing of trying to just build a better like servo loop around the existing motor, so I wouldn't modify the sewing machine itself. I would just like build a new control box that I would plug into it. And I just didn't have any luck with that because the motor itself was not stable at low speeds, and yeah, we'll get more into that. I think I'm gonna try to follow through with that plan. Is Tuco still out here? Oh, Tuco's still eating. Ah. Oh yeah, green screen beverages. All right, so first of all, this is my old blog. If you go to scanlime.org, you'll see that I've been like blogging up the videos that I've been making recently, but it's also just got a bunch of older stuff that I did. And this is something I made when I was living in the Silicon Valley, doing software stuff, and had time to do hardware hobbies to kind of balance out my life between the software obsession and the hardware obsession, which was my thing for most of my life, I guess. Gosh, yeah, I did make a video, but it's a very old video, and it's not so great. So yeah, this sewing machine, I think it was something I bought locally at a craft store. I think it cost like $120 or something like that. So, certainly not a high-end sewing machine or anything. It's mostly plastic parts, and I'm sure nicer sewing machines just start out with better motors, and you wouldn't have to bother with kind of overthinking the problem of improving the speed control. But both because I got a cheap sewing machine and because I kind of wanted to overthink the problem, I ended up going through this whole thing. So, yeah, the first thing I did, because I ended up like iterating on the motor control a bit as I wrote later, but the sensing aspect kind of, I kind of got something that worked pretty well the first time, so I didn't really have to iterate on the sensors. I needed two pieces of information: the motor speed, and I needed some kind of reference that I could use to estimate or determine its absolute position. So for the absolute position reference, I just used one of these photo interrupters that has an infrared LED and infrared phototransistor, and I just stuck it next to this existing part. I think, what is this? I think this is, so this is a cam that's attached to like the one main drive shaft in the machine, and I think this is part of what raises and lowers the, what are they called? The feed dogs under the presser foot. I could be misremembering because this was so long ago, but it was something like that. It was like a cam. It's like a piece that moves around sort of once per cycle that the machine goes through. So it doesn't really matter where that is in the cycle. It can, as long as it's at a predictable location, it could use that to estimate the angle. Um, yeah, I guess for some reason I didn't want to do a rotary encoder. Um, this is sort of a weird constraint because like it probably would have been fine to an encoder on there somewhere. But I think I was especially not wanting to mess with the mechanical parts, and I wanted to do something that was pretty much just attaching optical sensors to the existing mechanical parts. So that was an interesting constraint. So I did this thing with the IR sensor on the belt, and then switched to stick that on this sprocket. So it's really sensing the reflection of IR light every time a tooth on that gear goes. Like kind of more robust sensors that are based on counting gear teeth, they're usually magnetic. I mean, you can see this was a plastic gear on the original motor, but I think this motor has a metal gear. Yeah, and I mentioned this, but the foot pedal, so yeah, the foot pedal originally had this triac-based motor controller that works basically like an analog light dimmer and chops the AC waveform at a particular phase dependent on this variable resistor setting. So I just desoldered everything, hooked the variable resistor up to an audio jack, and that was that. Yeah, and then whole of building a my own like opto-isolated motor speed controller. And I just used whatever parts I had handy, which in this case was an old X10 dimmer module. And so I used just the triac and the snubber and some other stuff, and like the optocoupler from that. Oh, actually, that didn't have an optocoupler. Yeah, because like all of that stuff ran directly on mains. But yeah, then I just discovered that this was not good enough to operate the control loop in a responsive enough way. I was already having trouble with EMI, of course. I mean, I'm still no analog expert, but I was not as good at like locating and debugging like analog interference issues at the time, and I didn't really have a fast enough see a lot I was trying to track down. So yeah, then I found this beefy, like I think electric scooter motor at a surplus shop nearby. Are we having stream quality issues? Oh, that's neat. Tim on Twitch chat says that they learned from this blog post to use that same LCD a bunch of years ago. That's cool. Yeah, I remember back at the time I was making this kind of stuff, I would often kind of foray into like peripheral and microcontroller combinations and would end up just having to write drivers myself for a lot of the stuff. Gosh, that video is pretty glitchy over there. Oh, interesting. Let me try to do a brief detour to look at the video and see if that's all right. Building a fence nearby. I don't know if you can hear that clatter. Be able to tell if the stream is good on this tablet because the tablet itself is working too hard. Okay, a bunch of reports that there's something wrong with the video. Sorry about that. I don't know if the problem is on the encode side here. It'd be really weird if Twitch is working better than YouTube and Diode Zone. Because Twitch is like downstream from those two and does some extra processing. Like the way this works here is I have OBS on one machine sending the video to a local restreaming server, and that local restreaming server sends the same video out to YouTube, but locally transcodes it before sending it to Twitch so that it can fit in Twitch's bandwidth limit. Bandwidth. That's almost never an issue. I mean, I have so much upstream bandwidth there. Oh. What is that? Okay, maybe that's why it's choppy. You know, that might be a local backup of diode. I think something is going very wrong with the stream server chewing up bandwidth. Alright, I'm gonna restream. Really killed. Are we back? It looks like we're back on live.diode.zone/scanlime. Are we back? It looks like we're back on Twitch. Gosh, I have a theory about what was going on there. That was pretty weird. I think I've seen something like that before, but not that bad. Oh, now Tuco wants attention. Oh, now Tuco wants attention. Hey, Tuco! Gosh, he has great timing, you know? Gosh, yeah, so the Nginx server, its logs were full of errors. I think what was going on is that there was one error that started cascading. such that every reply generated additional errors until it consumed all the available router bandwidth. So yeah, maybe it's good luck to reboot that server before I stream. Gosh. Maybe I should also see if I can update my Nginx RTMP server. Yeah, I was panicking at first because I'm like, oh my gosh, is someone DDoSing me or whatever? But that's not even internet bandwidth. That's like internal bandwidth between my network and the network that my like internal network and the network that Diode Zone is on. That was fun. I saw it, our second glitch for the mission after the green screen falling down. Oh yeah, I guess I could talk about the dash. Sorry. Should not try to communicate while I'm fussing with my microphone. Yeah, I guess I could talk about the dashboard while I'm here. It is a pretty weird piece of kit. Maybe I'll turn off that camera we're not using or make it tiny. Oh, Tuco's coming back, so we don't want to make that too tiny. Oh, thanks for the video, both the bug report earlier and the confirmation that it's better, because, yeah, gosh. Let me make this a little smaller so you can see the whole thing. Yeah, I kind of went all out on the Grafana. I've been doing this for a little while here just because I mean, I run a bunch of services for myself and for friends. Like, I mean, I have like I've got a few public servers here. I've got the main Diode Zone server, the meet.diode.zone server. I've got a tiny DNS server. Anything else? I mean, I've got like an internal network that is separate from all of that and connected in some very specific and limited ways. But yeah, I've got this graph that just has CPU of like all the machines. This is like all the Wi-Fi clients. These are all the machines that are connected directly to the internet. So some of this traffic is like between those machines and each other, but some of it's going to be external internet traffic. The power graph is a little messed up right now because I haven't actually set up most of my power monitoring here. So it's just got a couple of sort of weird things and they're all mislabeled. Like the one that says Winch2, like that device used to be connected to Tuco Flyer, but now it's, I think, that's like all the studio equipment in this room. So everything in this room is drawing 300 watts right now. But I don't have those sensors on like the main server racks because I don't really trust them to pass that much current that much of the time because it's just going through a little shunt resistor, right? So for measuring the power usage of the bigger stuff, I've been estimating it based on what the UPSs will tell me. So these are like the big UPSs here. There's these big ones up here that are going to last like over an hour are on the public servers. And then there's like a tiny one in the garage and a little one that's, well, no, it's a pretty big one actually, but it's got a lot of stuff on it. So it's only going to last like 17 minutes and that's like workstations. And my complicated Wi-Fi setup, I think I mentioned before, but I have a bunch of separate Wi-Fi networks just for network partitioning reasons. And so I've got them organized by like what network it is and then what like VLAN it's on. And then these are all the different networks that go through the router and get like firewalled and bridged and whatever. Oh yeah, Tuber is the name of the server that PeerTube runs on. So yeah, these are jobs in the PeerTube job queue. So like these were video uploads and transcodes earlier. And these little blue spikes are activity pub traffic going in and out of the server. I would not necessarily have separate graphs for the Linux and the Windows temperatures, but I set my database up in a way that turned out to be bad, and I need to fix that. There are like different hardware monitoring clients for Windows and Linux, right? And I, for privilege separation, just put them in separate InfluxDB databases. But it turns out that, as far as I can tell, I don't think you can have one graph that pulls data from two different databases in Grafana. So yeah, What else do I have that I could... Oh yeah, I have a separate dashboard just for the meet.diode.zone server. So we are using 15% CPU on the chat server right now. It's pretty light. I mean, this machine is super underpowered, but I think somebody's running like some kind of like school class here with like 30 students, and it's hitting like 60% CPU and not even 10 megabits of bandwidth. But this is a very underpowered server. This is like basically a laptop motherboard that was just some random thing I found, so it kind of needs an upgrade. Got a whole dashboard for the server running PeerTube. There was that bandwidth catastrophe that just happened and knocked us offline. These other rectangles of gigabit are backups, so like that's why my first thought was it's doing a backup. I don't know if this power is not accurate because this is actually connected to a different UPS now, but I did have a power graph that was based on the data from the UPS. Oh yeah, all the disk temperatures, ZFS caching. Yeah, I've got two big ZFS file servers here. There's the one running the PeerTube site, and then there's my internal NAS, which is, I just call it FileBox because it's the thing that all the files are in. And this is like where I store my video mostly. And it's just a big pile of disks. Anyway, I could take questions about any of that, but the main topic at hand, I guess, was the sewing machine. We can get back to that. This motor was a pretty lucky find. There's this place that, gosh, yeah. I mean, it's kind of sad because like all these surplus shops in Silicon Valley closed down pretty recently. Like there's this place called Weird Stuff, and this other place called Halted Supply. And so Halted is where I got these. You know, you just go in there and then have like racks of like weird telecom equipment and, you know, just computer junk, and you can pick through the bins and get interesting finds, and just bins and bins of like capacitors and raw components and stuff. Question from AR about Wi-Fi partitioning, why I didn't use WPA EAP and push clients to separate VLANs with that. Guess I hadn't considered that. Might be something to look into. I mean, I didn't necessarily want to have that much granularity because, I mean, it kind of makes more sense to me to separate things into like a couple of different VLANs that are for different purposes. But yeah, that might be something to look into. I generally don't put a whole lot of like trust in just like having a Wi-Fi connection. So like stuff that's really important, you know, even if you're on Wi-Fi, you'll have to also be on a VPN. But yeah, you could always have more VLANs. Never have enough VLANs. Oh yeah, and so this motor seemed pretty much perfect. I thought it would fit in the original chassis, but it didn't quite, so I ended up having to kind of hang it off the side like this. Oh gosh. Yeah, and I really didn't know what I was doing with motor controllers at the time. Because even though here I'm like, oh, it'll be easy because I'm using this chip that does all the work, like there's a bunch of stuff that I didn't do correctly because I did not understand motor drivers at the time, really. Yeah, and I was using, so like you can tell already looking at this picture, like, this is obviously not good. Like, do you see any significant capacitance next to the motor driver chip? There's a couple of these, but those are for the charge pumps. Like that's not actually carrying any of the load from the motor. And then this is the main drive capacitor, which is a beefy electrolytic, but Like, I mean, who knows what the ESR is of this capacitor? I'm pretty sure I didn't spec it for low ESR. And then look at these wires just flying all over the place. Like, this is not a good motor driver, which I did not know that at the time, but it is not a good motor driver. Oh, that's a good piece of advice from Jenny. She uses WPA EAP for her main Wi-Fi, but the device support for that is lacking, so there's some separate IoT and guest networks. Yeah, I've got kind of a separation where I've got like a sort of main network that you can like print from it, that kind of thing, and then I've got like a guest network that's only internet access and more restricted, and then I have like an IoT network which has all the like power sensor things on it, which isn't connected to anything except to the software that talks to those. What else? I've got a network for like completely experimental stuff that usually just only has one project on it. So yeah, that's going to be a problem. And also, like, here's the DC-DC converter. I just like took apart like a car charger, so it's all just like random junk. And yeah, the original iteration of this, I didn't even have a user interface. I had this, so I had this motor controller box. I had, not that, but, did I not even have a picture of that in this original blog post? My ancient Flickr account. Oh yeah, this was the prototype of the amplifier for kind of filtering the results of this reflection sensor. A little interrupter, all point-to-point wiring. And that was the, yeah, this was the dead end. Oh yeah, that was a breadboard of the microcontroller portion of it. So the other thing that's weird about this, so there are many things about the sewing machine that are just weird and ridiculous, but one of the many weird, ridiculous things is that it uses the propeller microcontroller, which is something I was sort of fascinated with for probably too much of my life. But it's sort of a weird little processor. Like, it kind of fits my aesthetic of, oh, it doesn't need to run anything standard. It just needs to have an interesting architecture. So like, it didn't even have a C compiler until fairly recently. It natively runs assembly language. It's got its own flavor of kind of RISC 32-bit instructions. It's a very kind of weird architecture. But then, yeah, then it's also got this built-in ROM-based interpreter for this language that they call Spin, which is sort of like this weird amalgamation of like Python and BASIC, and it's very strange. And it's got hardware sort of multi-processing support where there are 8 symmetric cores that each have local memory and round-robin access to shared memory. And both the assembly language and this sort of basic like Spin language let you sort of launch processes on additional cores using that hardware multitasking. So yeah, it's a pretty weird processor. I like it. Well, I mean, I shouldn't use past tense. Like, I still like it. I just haven't had an occasion to use one for a while. But I like it because it's kind of blurs the line between what you would normally want to do in hardware and what you'd want to do in software, and lets you just like write code to pretend to be hardware, which is one of my morbid fascinations. And you could easily implement protocols in software by either just like bit banging them directly by like manipulating the I/O pins with CPU instructions and timing it really carefully. Or there were some built-in peripherals that helped with that. For output at least, you could use this video generator peripheral that each core had, which was basically a shift register that you could adjust the timing of. And there were also some fairly powerful timers connected to a PLL that let you multiply frequencies up into fairly high ranges for a microcontroller. So you could use those PLLs to do things like transmit FM radio, like from the microcontroller in software. So it was a great microcontroller for doing tricks that would land you on the front page of Hackaday or something, which, you know, is a good way to get a bunch of nerds excited about a weird microcontroller architecture, I guess, right? Oh yeah, I did briefly experiment with the AVR butterfly as a UI option, but I didn't end up going that route. I don't know where my AVR dragon is. I think I loaned it to someone and then never got it back. Oh gosh. Here I was using an ATX power supply. Yeah, I don't think that worked very well. Oh yeah, so the sewing machine came with this LED light, which you can see has a capacitive dropper, bridge rectifier, fuse, just like a very minimal AC powered LED lamp arrangement. And so I could just take out all these components and just wire up some DC to the lights. So I think that's what I did here. Yeah. Gave it the same treatment as the pedal. Remove all those unclean AC components, leaving only the diodes. The original diode zone. Yeah, so this motor driver box I think is going to be our first step because there's just a bunch wrong with this that we need to address. That's the speed sensor that I ended up using. So it's detecting the optical reflection across these teeth as they go by, and it's just positioned very carefully. Here's the ugly point-to-point wiring on the bottom side of this board. Hey, don't be ashamed. You gotta get the signals from point A to point B. You don't want to etch a circuit board. It's okay. Just let that 30 gauge wire fly. And sometimes you got to use a piece of coaxial cable just to keep the signal integrity good. You know, it's all right. That's the IR receiver. I think it was a phototransistor in that reflection sensor going into the input of this amplifier. You'll often see these reflection sensors used in just like a binary on-off sort of way, and just wired directly into a digital input on your favorite microcontroller. I was using this in a somewhat more sort of somewhat edgier way, where I was trying to just like amplify the heck out of a weak signal and then bandpass filter it to get just the spectrum that I was interested in. I forget exactly how I did that, but I've got these great hand-drawn schematics. So I called this the tachometer amplifier. So that was the op amp, resistors and capacitors. Got to keep those feedback paths manageable. Sewing machine 2.0. I guess 1.0 was the one based on the AC motor. Oof. Yeah, so this is what's in the box. I've got the banana jacks. The best way to get power into any project is through banana jacks, right? I don't know where I got this 3 amps. But yeah, I just kind of used this brick DC converter. I assumed that this would be enough capacitor. Oh gosh, I bet I've got some of the nice capacitors that I got for Tuco Flyer left over that I could use for this. Yeah, and then here I'm just like, all right, little piece of silicon, you can do all the work, and it just needs a couple of tiny capacitors. But yeah, so like the problem with this is the motor. There's a bunch of noise coming from this circuit. The motor itself has brushes in it because it's a DC brushed motor. And then usually more significantly, there's a ton of noise coming from every on-off transition as you just slam the power on and slam the power back off, which is what you want to be doing for that nice Class D amplifier efficiency, right? But that creates a lot of inductive ringing in the motor. It also just creates a bunch of switching noise from that hard edge. So it's just sort of instantaneously trying to draw a bunch of current from your power supply, which is what this capacitor is for. But capacitors are not ideal, and just like a big chunky electrolytic capacitor isn't usually going to be able to sustain just a nice steady voltage level and handle that current inrush up into the high frequencies where these noise pulses are going to be a problem. So we should take a look at that, and I suspect we're going to have to put whatever ceramic capacitors we can find and maybe tantalum much closer to the motor driver physically. Gosh. I think that's spam. So yeah, I think we're just gonna need to put some capacitance that can actually like handle some of that current pulse. It might also be worth putting a capacitor just like across the motor, just to keep the commutation noise from the brushes a little bit more under control. And then the other problem with this is that we're just kind of plugging the microcontroller directly into this motor driver chip. And so like any noise that makes it through this chip into, say, the whole ground of this part of the circuit, or maybe somehow couples through the power rails into these control lines, maybe through the ESD diodes, that's just going to transfer that noise pulse right into our microcontroller. And it's not going to be great for the software running on that thing. So, or the hardware. So that's something to watch out for. I guess I'm jumping ahead a little bit, but I went ahead and tried to address this, and I blogged about it a little bit. I thought I fixed it way back then. When was this? How long has this bug been in limbo? Oh, that was just later that same year. So that other blog post was from January. This was from October, still 2010. So yeah, I thought I fixed this like almost 10 years ago still. And no, I just added some grounding, and what else did I do? I think I added some series resistance between the microcontroller and the motor driver, which, that will make the noise pulses less effective at crashing the microcontroller, but it's not a great solution. So like this was definitely like a half-baked solution to my problem. So I just have like a wiring diagram. Oh, such classic graph paper. So yeah, it was a phototransistor down here. And I just used a little separate FTDI breakout board for programming the propeller chip. And then this is the actual thing. Make a massive SMD ceramic capacitor skyscraper. Yeah, it might come to that. I've been trying to like unpack all my junk since moving, and I have most of my components, but there's still probably some stashes of surface mount capacitors that I've yet to fully locate here. So yeah, the propeller. So the propeller is a weird chip. Most people would use it in a modern like TQFP package, but it was still released in a 40-pin DIP as well. So you could prototype with just a regular breadboard, just plug that big ol' sucker in, big 40-pin DIP, just like the 80s, And then you need very few external components. So the usual decoupling capacitors, an external crystal. It's got an internal PLL. I think it's even got internal load capacitors for the crystal. It does need an external EEPROM because they didn't have a they fabbed this like themselves on a shoestring budget, and so they did not fab any flash memory. They just have RAM and then external flash memory. So it loads from a E squared prom. How do I zoom out? I guess I have to zoom in twice and then zoom out. That is a weird UI flicker. Oh yeah, I needed to filter the reset pulse from the FTDI board into a reset pulse that, so like if it was in a steady state, I didn't want the microcontroller to stay in reset. So this is a AC coupling for this DTR signal. So when there's a rising edge on DTR, it'll pull the base of this NPN transistor high and then pull the reset line low. Why isn't there a pull-up on reset? Is there an internal pull-up? I think there must be an internal pull-up. Reserved for TV. That's right. You can also generate like NTSC television signals pretty easily on the propeller. So one way I had of debugging this was to plug in a little dongle that had some resistors on it and then connect it to a television. If I wanted more real-time debugging than the serial port. But that was before I added the LCD. Is the LCD even on this schematic? I don't know if I even made another revision of the schematic that included the changes that I added, or that I made, like the LCD screen. Yeah. Oh yeah, and then 3.3 volt regulator. It is at least modern enough for 3.3 volts. That's the E squared prom. And there's the tachometer amplifier. So what was I doing here? So this, can I stop scrolling this? I want to embiggen it without the auto scroll. Whatever. So this resistor here was providing a bias for the phototransistor. So when the phototransistor was not conducting, this voltage floats high, up to 6 volts. But the more the phototransistor conducts, the more it pulls this down, sort of against this 10K resistor. And so this is, using a resistor and a transistor like this is sort of like a really simple amplifier. And you can adjust the gain of the amplifier by changing the resistor. So this is a little higher gain, I think, than you would often use for just like a light dark sensor. But then there's a couple layers of amplification here. So I AC couple it, and then this is a little RC low pass filter, I think. I didn't like write down the frequencies or anything. And what is this? This is just like a regular inverting amplifier. So here, these two 10K resistors and the 0.1 capacitor are making a virtual ground for the positive reference. And then there's one other thing I did wrong in this circuit. So this is a nitpick, but it's good practice to keep the impedance of the two inputs on the op amp pretty similar to each other. So here, like the negative input is seeing like whatever this turns into, like probably close to 270. And then the positive input is like more like 5K impedance. So, that's not a huge difference, but this is pretty high gain amplifier though. So this feedback resistor is much larger than the impedance of the input here. And then this says hysteresis, so I assume that's what I'm doing. This is a positive feedback amplifier with an adjustable threshold from this variable resistor. Or what is this? This is it adjusting the amount of hysteresis? Yeah. So this adds hysteresis. So if you imagine that this part of the circuit with the variable resistor wasn't there, this would just be an inverting, what would it be? It would just be a comparator that compares the negative input to this half VCC reference. So I'm trying to have a digital signal that I can feed to the microcontroller here. So a comparator is sort of the behavior I want, but hysteresis kind of keeps it from kind of acting indeterminately at the boundaries, because you'd get a bunch of noise, you'd get indeterminate logic levels, you want it to sort of snap one way and then snap the other way. So the hysteresis, this variable resistor just controls like how much hysteresis there is. You can kind of think of this resistor as sort of pulling the positive input of the non-inverting input of this op amp up or down a little bit, but it's forming kind of a voltage divider between this 10K, or fraction of 10K, and the 500 ohms that you're seeing here. So by kind of changing that proportion, you change like how much this positive input moves every time the output changes state. What is this 270 ohm for? Oh, that was my lazy. Is that really all I did? I think I was trying to. Yeah, that's not great. I think that's for level shifting, but I should really use a larger resistor value for that. That's working on the theory that you can make anything 5-volt tolerant if the current is low enough, but this is not really a low enough current to get away with that. So I'm kind of stressing out the IOs on my microcontroller a little bit with these. So yeah, that's R8 is a level shifter. I hope I changed that, but I don't know if I did. We could just redo all this, but I mean, we could also do a simpler fix. That was the old triac thing. And here's the big old ribbon cable for the LCD. So yeah, the first blog post sort of ended with, this is interesting, maybe it'll eventually be a CNC something something. But like it didn't really have any UI. It just had the pedal, and you could load firmware onto it to sort of change what it was doing. So I had one firmware that kind of just made it act like a normal like sewing machine pedal that controlled the amount of power the motor got. But then I had another firmware that did a servo control loop. So the pedal was taken to be not the power level of the motor, but the actual speed. And then it would automatically adjust the power to the motor so that you'd maintain a constant speed, which was really what I was after. But I had just like a separate firmware for that. I couldn't change it on the machine. So then I think the next thing I did was, yeah, I made a user interface for it. So I just got this, what was this, like some kind of Nokia LCD from SparkFun. Oh, I was talking about making my boyfriend plushies at the time. Good times. Okay, Nokia 6100. Do any of these links still work? Subversion repository. I'm still running this. I mean, I migrated this all to GitHub, but I didn't actually take this one down. Demo video. Oh, this is so old. I shot this like 2 cameras ago in 640 by 480. This is actually using a font that's built into the propeller's ROM. And the font is a different size than the character cells that I wanted. So you'll notice maybe that it's a little bit fuzzy on the edges. That's not what I wanted. That's because I wrote like a special purpose scaler just specifically for this ratio to just blit those pixels on as fast as possible at that scaling ratio. And I thought the fuzziness made it look kind of anti-aliased and not bad, so I kept it. The alternative would be to have a font on there that was made specifically for it, but then that uses up all this memory, and you've got that ROM font just sitting right there. Oh, did I close the wrong window? don't know why it didn't show up in the other. I guess I didn't tag this blog post correctly. Anyway. I forgot that I was thinking about this. North skirt. Does that link still work? It does. That's cool. That was a fun project. I guess this blog post was pretty light on the details. I was mostly just like, I wrote a driver, check out the forum thread about it. Yeah. It's got to have a Kirby, right? Like, that's the most important part, is the Kirby-based speed indicator. The Kirby was not in ROM. I had to store the Kirby in RAM. Yeah, and then third blog post about the EMI problems, in which I fuss around with it and don't actually fix anything that needed to be fixed, really. I added a little LC filter. Oh gosh, that was also a problem, huh? So I guess the LCD or the DC-DC converter on the LCD board was, I think it was actually just broken. Like, I think I just had one with like a bad capacitor on it because it was just super noisy. This is just add a electrolytic capacitor. Why not? Yeah, and then I have all this stuff in GitHub now, not just Subversion. 4,096 colors. Oh gosh, this was also legitimately a weird piece of code. Why do I write stuff like this? This was just hugely weird, always. Ugh. Blend table. Yeah, that was the weird scalar I was talking about. A cog is what they call the sort of 8 separate processors in the propeller. So this language is Spin. That's the sort of basic-ish thing. It's like object-oriented basic, kind of. So here we're defining constants. It's a fairly simplistic language in that it doesn't have high-level types. It doesn't have like structured data types, really. So it turns out that that's not as much of a limitation in practice, because the other limitation that you often have in writing spin code is that you need to segment your design between the high-level spin code and the low-level assembly code, because you inevitably, if you want to do anything that's like tricky I/O or like fast processing, you end up using assembly because spin is interpreted and pretty slow. The reason to use spin, besides it's quick to write, is that it's also easy on the memory. The spin opcodes are just these little 8-bit, short interpreted codes for a stack-based machine, whereas the actual instruction set is pretty heavy duty. Like, it's these giant fixed size 32-bit opcodes. You have limited amounts of RAM in each cog for that code, 512 words or 2K. So yeah, the actual assembly language limitations are fairly important in this architecture also, if you're trying to write something that kind of does something weird, or like, is sort of like edgy, that tries to get the processor to do something weird, or that's like on the edge of what it can do, like this. So, I find, and this is not just me, but like a lot of the code that the creators of the propeller wrote to demonstrate it kind of just has these conventions of how you pack things into 32-bit words, and then you have constants that are related to those conventions, which you can share between the assembly and the spin code. But there aren't just like shared code or shared types. There's just like shared numbers, and then you have to sort of make everything else up through discipline. It's a bit inconvenient if you're used to just being able to write C code and compile it to every part of your system, but it was certainly the source of some interesting challenges and some really strange designs at the time. So this is spin code. It's got these functions that sort of act like static methods. So each module kind of acts like it's a singleton object in this language. Like you could instantiate multiple like Nokia LCD modules, but they would effectively just be like two copies of the same thing loaded into RAM separately. It doesn't really have a separation between code and data. It just lets you instantiate the code and data multiple times if you wanted to. So these act sort of like static methods, and these act like constants, like static integers. These also act like class variables or like static variables. They exist in RAM once. Like you can't at runtime like instantiate multiple LCDs and have them each have a different copy of these variables. Like this is purely a compile time kind of object model. So there's stuff like this where if this were like C++, I could write some kind of expression that's like based on a library that abstracts away some of the details of the individual processor to some extent. But this is just a different environment. Like none of this is intended to be portable. So it's all just like referencing stuff fairly directly, and there aren't a lot of opportunities for abstraction, which is it's interesting. Like it kind of gets old after a while, but it's also it kind of keeps software at a low level of abstraction and kind of down to earth, which makes it a little bit easier to use as a teaching tool sometimes. You can always lose that benefit by making the code obscure enough, but it's interesting to use tools that place limits on the complexity sometimes, both for kind of like demo scene impulse reasons and also for educational reasons, I think. So this is already doing like multiprocessor things. So like this code, for example, would be called on the main thread of execution, really. So like one of the processors would be running the spin interpreter and doing just like a bunch of this sort of main program kind of stuff and doing the setup. And at some point it would just transfer execution to this routine. It would run on the same processor, just like using some stack space temporarily. But then when it gets here, this cog new, this is like a command in spin. It turns into an instruction that the interpreter runs, but then the interpreter under the hood there's like a CPU instruction that just loads up a new CPU. You just give it the address of some code, and it like dynamically allocates a CPU core to run that code just as a single CPU instruction. But in this case, the spin version of this allows you to either run assembly code or spin code. So if you call this with spin code, the compiler will generate a version of this that launches the spin interpreter in a new core and just has it run starting from a particular function. But in this case, I'm actually giving it the address of some assembly code, and this is just like a parameter, which in this case is the address of a command variable that I'm using for inner core communication. And so this takes the code at this address, which is way down here in EEPROM. This is not a good simple example because this is a very strange piece of code. But so this is where it starts copying from. So, and this is actually resetting the assembler's idea of what address this is to be like, this is going to be loaded at the beginning of memory. So everything kind of moves from non-volatile memory, EEPROM, then into shared memory, and then finally into like local per core memory. And so this is the process of migrating, 1 up to 2 kilobytes of assembly code chunk from the shared memory into the per core memory. There's a little hardware state machine that does that copy and then starts it running. So it starts copying from here into that internal per core memory, and Does it just copy the whole thing? I don't think we give it an end. I think it just copies a fixed number of instructions. So it always just fills up the internal memory. But, as soon as this runs, this starts that other core, copying the memory and then running after the copy's done. And so we can just spin and wait for some memory to change to detect that the other core has made it to whatever point we want it to make it to. Do some bit bang IO. So then the rest of this, like the general structure that you see in a lot of this code is you've got some interpreted code that sets up, like kind of a higher level API for what's going on. So in this case, you do the initialization in the interpreted domain. You do these sort of, kind of high level methods like start, stop, command, whatever in the interpreted domain. So you have this kind of slower but also more compact interpreted code. Figure out stuff like how do I encode this particular argument list in a 32-bit value and just like smash stuff together, or like, what turns into what SPI command. You can update color blending tables and stuff like that in code that doesn't have to be high performance and can just be sort of quick to write and small in the memory footprint. But then when it comes to, stuff that's actually really time critical, like in this case, bit banging SPI at 10 megahertz, we just want to do that in assembly code. So this is especially weird because, gosh, how did this even work? I don't know if anybody ever wrote a faster SPI engine than this for the propeller, but it's just such a weird piece of code that I don't know how many people actually ended up using it. This is that's just like blending stuff. Oh, this is the ROM font blender. So yeah, text 8x16. The initialization overlay. How does this work? This is some code. So I keep mentioning the memory hierarchy here. There's this little chunk of memory, just 2 kilobytes per core. That's the only place you can actually run instructions. Like none of the other memory is connected to the instruction bus. So it's actually not that much space, which is why like spin. I just noticed the question about how the audio bits of Blue Button are being used. I'm using that for if folks want to have like audio chat, we can do audio chat. So I have like if you connect to Big Blue Button and enable the audio, you should get a copy of my microphone. But then like you could also enable your microphone if you want. We can have a chat. And similar with cameras, I don't think I have the camera set up right now, but like if we had Tuco in front of the Wi-Fi camera, I can send it over. Oh. Yeah, I don't know why I'm going this deep into the propeller code. I don't know if people are interested in it, but it's a very strange chip, and there is some really weird code that I wrote for this chip. Like I wrote so many strange things. Like I've bit banged. And if you don't know what bit banging is, it's like writing code that just toggles pins on and off in order to communicate at some higher level protocol. And that line is kind of blurred a little bit with the propeller because the propeller gives you a little bit of hardware assistance in the form of a video generator that you can use sort of like just an SPI, or not an SPI, but like sort of like a shift register that you can just send bits out at a predefined rate. It gives you a couple of oscillators that you can adjust to even generate pretty weird frequencies. But yeah, it kind of encourages you to do a lot of strange things in very tightly written assembly code, which was something that I've often enjoyed. So like these are all commands which you can invoke by writing like a command identifier into some shared memory, and then the processor cog that's doing the SPI will read that command, then start running assembly code using the parameters and specifically copying any inputs that it needs out of the shared memory. But this one was pretty weird because I think I needed to have some like Yeah, I mean this is like self-modifying code. I've used this trick in multiple drivers too. I wrote a whole Ethernet driver using this method. So where is the entry point? Let's just start from the actual entry point. So we load this chunk of code starting from here. This piece of code is not actually the driver. It's a loader for the driver. So we used the cog_new instruction to copy the memory starting from here into that 2 kilobyte per processor memory chunk, which kind of takes a while because the shared memory is slow. But then once we make it there, this is, there's actually a fairly widely used trick in propeller assembly called large memory model, which if you've ever done any DOS programming, that might already be sending shivers down your spine. But it's different than DOS. Like in DOS, there were these different memory models you could use, like large, medium, and small, which were depending on like how you did your segment addressing. So it depended on whether you could access your entire program's data and or code in a single 64 kilobyte chunk, or whether you needed to manage multiple separate 64 kilobyte chunks of memory. Because this was a 16-bit system, you couldn't just directly address more than 64 kilobytes. That was just not possible. But they had these segment offset pointers that let you add another 16 bits to say which 64K you want. And there's this whole thing. Yeah, so that was DOS. This is different. This is kind of inspired by that, but it's more about the distinction between the shared memory and the local memory. And in large memory model for Propeller, you're just fetching every instruction that you're going to execute out of shared memory, sticking it in local memory, running that one instruction, and then fetching the next instruction. So you're like writing a fetch loop in assembly language to fetch assembly language instructions. So it's very slow, but it lets you directly use a lot more memory than otherwise. So this is a variant on that, which, what is this? Instruction destination. Yeah. So this is a loader, which takes code from init data. Where does this start with? Gosh, I have to like page back in my knowledge of propeller assembly because it's been kind of a while since I've done this. Maybe we'll go through this slightly more methodically with the benefit of some additional hydration. Because, gosh, propeller self-modifying code. How did we get here? Why does my sewing machine have self-modifying code? Wonder where Tuco is hanging out. Tuco has some favorite spots. Oh yeah, Tuco is next to the servers, enjoying some of that warm air on this warm day. Yeah, it certainly might get old. So far, I kind of like living somewhere warmer. The old warehouse was always cold. This room is warmer than the rest of the house on account of that 300 watts of studio equipment. And this tablet that's apparently working very hard. Gosh, so this is all weird. This is all weird. So this might be a little bit familiar to folks who know ARM assembly or other like kind of more RISC architectures. Like, so you might recognize these condition codes. Every instruction. This is like full strength ARM, not thumb. Like every instruction has its own condition code. The instructions all have a very regular format. So there's always an opcode, a source, and a destination field. Let's actually bring up the manual. That's it. Thanks, Duck Duck. New improved. Where did that come from? So, gosh. This is such a weird chip, but I am still so fond of it. Concept. High-speed processing, low current consumption, small physical footprint. All the stuff engineers like, right? Flexibility and power through its 8 processors that can perform simultaneous, independent, or cooperative tasks. Flat memory map, asynchronous events. Yeah, so this processor also has no interrupt controller. It totally relies on instructions that wake and sleep cores based on events. Bunch of completely symmetric I/O pins. So that's the thing. It doesn't have hardware peripherals, and all the I/O pins are the same pretty much. Sometimes you'll find restrictions based on software support. So, like some of the code that I've written, for example, takes advantage of instruction encoding tricks that let me do that let me access, like, for example, pins 0 through 7 more efficiently than the other pins. So, you'll see stuff like that, or you'll see stuff that's just been hard-coded. And for example, this is stuff that's hard-coded in the bootloader. So there's a ROM bootloader, which implements I2C in serial, and so it does it on those particular pins. But that's not because there's anything special about those pins hardware-wise. It's just that's what the bootloader is coded for. It's a very weird chip. And it's pretty fast, too. 80 megahertz. I've also overclocked it to 96 pretty regularly. I wrote a USB host controller for this chip that overclocks to 96 megahertz and bitbangs full-speed USB. Which, again, it was a piece of software I spent way too much time on, and I don't know if anybody actually used. It was pretty weird. Yeah, pretty minimal. You just need to add memory, a crystal, and you can program it with a serial port. Cores. Yeah, so the IOs are just wired up to all the cores symmetrically. And then each one has a 512 by 32-bit RAM. And then there's a central memory controller over here, bus sequencer. They call that the hub. Yeah, this is always a fun diagram, right? They kind of think of it as a little rotating hub that provides periodic access to the shared memory. So you can get really into the optimization here and write code for the individual cogs that takes advantage of these access slots. So if you do, and I forget how many cycles it is. It's been way too long since I've done this, but like you can count cycles and time it so that the accesses to the hub occur when the hub is ready, so that you don't have to wait very long. It's always kind of fun. Oh, totally. Yeah. So the Arbiter says that it sounds very much like a lovely playground for kind of old school hackers, whatever that means. Yeah, no, it's definitely like that. Like a lot of folks who are into retro computing are also into the propeller because you get a lot of the same kind of vibe from it. And, it's even a good kind of adjunct to actual retro computing. Like you can stick a propeller on, a Commodore 64 or something and do interesting things. I think there's actually a really good emulation of the SID that runs in the propeller. I could be remembering wrong, but that's like the kind of thing the propeller is actually really good at, like stuff like sound and there are other processors that you'd want to choose if you want professional digital audio or something. But if you want to do like weird hackery sound projects, this is actually a pretty cool chip for that. Yeah, I actually have always wanted to make like a hardware, tracker module player for some value of hardware. Like I think when I was a kid thinking about this, I would imagine building it out of EEPROMs, like old school erasable, like windowed EEPROMs, and hooking them together so that you would, have. I think I was just planning on using like EEPROMs and digital logic somehow to make like a little wavetable synthesizer. I don't know how I would have gotten 4 channels out of that without just like a suitcase full of TTL chips, but I didn't have an FPGA at the time, and I thought that would be interesting. So that never left the drawing board, but it'd be interesting to do that with an FPGA now. I mean, I'm sure it's been done, but it would be fun to do it myself. Oh yeah, and then Laura mentions the propeller too. Yeah, folks. So like they've had a sequel to this chip in the works for a really long time now, and folks are excited about it. But it's also been a long time, and it's kind of hard to tell like how that's going to be and when it's going to come out. But it seems like they're really shooting for the stars there. I haven't looked at it closely, but I think someone was saying it. Like the propeller one, you can generate like high res VGA. You can generate like analog television signals, stuff like that. I think they're shooting for like HDMI and USB 3 kind of protocol level on the propeller too. So that could be really tasty. And then to answer Jarrett's question, so Jarrett asks if you connect to the propeller over serial and then it programs the EEPROM for you. Yeah, so there's that bootloader in there. They actually released the bootloader as open source eventually. For a long time, they were like, "Oh no, the bootloader, that's our secret sauce. We don't want anybody to see the bootloader." And then someone like extracted the bootloader. I forget how, and then they were like, "Okay, fine, we'll open source it." And of course, the code is super messy, but it's also really, really compact. It's like very, very tiny. I think they talk about the bootloader protocol in the manual. So these things that they call registers are actually just the COGS 32-bit RAM. So these things that they call registers, like you're running all of your instructions from these, but you can also read and write them as easily as anything. So like there's no separation necessary between code and data on this processor. There's no cache that you have to clear. Like there's no penalty for I think the very next instruction, you can't modify that because it will have already been fetched. So there is pipelining, but there isn't like an instruction cache or a data cache. So self-modifying code is encouraged in this architecture. It's very good for self-modifying code. The standard way to do pointers, like indirect memory accesses, is self-modifying code on this architecture. You just like modify the destination field from an instruction. It's the Wild West out here. They did eventually write a C compiler for this, but the C compiler took a while because it's a very strange architecture. Yeah, the early C compilers were just these like. So I mentioned that large memory model thing where you just fetch each instruction separately right before you run it. So they were all based on that because even trivial C programs would compile to be way larger than the cog memory. I don't know if that's still the case, but yeah, it's still not going to be really fast. Like this chip really shines at running custom written assembly language, and it's slow at everything else. Like you don't run something on a propeller if you just want it to be fast at running C code. You use one of these if you want to write a really, really strange piece of assembly language that everyone is surprised even works. So this is the like basic round robin timing. You have these 8 clock cycle windows that you can do transfers in. Hmm, 32 I/O pins, 28 of which are entirely general purpose. 4 have a special purpose at boot up and are available for general purpose use afterwards. So that's another thing that's kind of interesting and quirky about this architecture is that the default way that you use memory is that you store your entire program as this flat binary in the EEPROM, so 32K of EEPROM. It's got 16-bit addressing, and you have 32K of RAM and 32K of ROM. The ROM has the bootloader, the spin interpreter, and the font, and like trig tables, and like mostly trig tables. There's a lot of trig tables in there. If you want to do like an approximate sine or cosine or arctangent or something, they've got you covered. You have to write the lookup routines yourself, but you've got the ROMs with the actual values. It's kind of funny that they didn't put the code in ROM, But I mean, you can't actually execute code directly from ROM is the thing. You have to copy it into the hub RAM because that's the only memory that's connected to the instruction and data bus. Yeah, it's pretty weird. Actually, can we look at that code? Because I remember that being very interesting. Oh yeah, I forgot to mention they released not only the ROM, but they eventually released the actual like Verilog code for the chip. So you can just synthesize this onto an FPGA now and play with it. It's they're still like available to buy and like you should support them because they do good work. But like if you wanted to do an FPGA project based on the propeller, they've got this awesome project now. Yeah, it might be fun to hack around on this. I wonder if I can make. I don't know. I shouldn't get myself started because I could go so deep into something that no one would ever use. It would be very easy to do that. I've been there before. It's dangerous. Anyway, this would also include. Does this not have the link to the actual Git repo? Is this just a press release? I want the actual code. This is what I wanted. Yeah, so are these? I think that's spin code, is it? Oh yeah, the original Peanut was the code name for this before they called it Propeller, I think. Oh yeah, this is the stuff. There's the EEPROM programmer. It's just very straightforward. Good old decrement and jump if not zero. It's the best way to loop. Right, like you can just set the clock frequency with an instruction. It's great. You could just launch an interpreter with an instruction. This is such a great architecture. These are not macros. These are all instructions. Of course, call is an instruction, right? You don't think it's like doesn't quite hit your traditional RISC instruction set profile. It's kind of more designed to be like straightforward and not necessarily efficient. But yeah, that's the ROM. It's pretty weird. Oh, is this doing baud rate detection? It is. The protocol is so weird, man. They also use this weird LFSR based thing to checksum. I mean, this is totally my shit though, right? Like the esoteric like assembly language tricks just to get the thing to boot. Like, oh yeah, I eat that stuff up. Oh man, don't make me bring out my boot sector. I've always got a weird boot sector that I can scare people with. 512 bytes of hell. I mean, it's a partition table and page tables. Yeah, so you mean you can just do all sorts of I/O bit banging. The bit banging is very good here. Oh, this is the shared memory map. So yeah, half of it is just RAM to do what you please with. So what I was saying earlier is that this is just copied straight forward from the EEPROM. So whatever it finds in the EEPROM, it just splats it right into the RAM and then runs it. And most applications don't bother to talk to the EEPROM unless they need to like store non-volatile stuff specifically. Um, there isn't like built-in stuff in spin for like reading and writing values. It's more just treated as like program storage, but of course you can use it. And one of my favorite pieces of code for the propeller is this demo by LFT, who you might recognize from other microcontroller demo scene productions. But yeah, what was his called? Turbulence was the name of the demo, and it was just so clever. Like it didn't use any of the standard development tools for the propeller, which are all like geared for simplicity rather than efficient use of the resources. He wrote his own development tools from scratch. He wrote the whole thing in assembly language, and he wrote his own loader for it so that the EEPROM could have mostly compressed data, which was loaded in batches. And then as it went from scene to scene, it would decompress the data it needed into RAM. It was great. It's like a really satisfying use of the hardware, but completely not the way Parallax designed this chip to be used. So you can do weird stuff like that with this architecture and do creative things with the central RAM and the EEPROM. You can even use giant EEPROMs. You can use SD cards, whatever. I mean, the sky's the limit. Or, I mean, 80 megahertz is the limit, really, but maybe 96. I think I've seen people pushing this into the low hundreds, but yeah. I mean, with the FPGA, maybe the sky's the limit, or your FPGA budget. Oh, and then I guess a full quarter of the address space is that font, which I took such pains to use on my differently sized LCD. And then trig tables, log and anti-log, okay. And then the little bootloader at the end. This is the font. It has a bunch of fun line drawing and schematic drawing symbols in it, but it's not especially international. I mean, you do what you can with 8 bits. Oh yeah, and of course, because it wasn't a weird enough architecture, they have to have like a planar bit store mechanism for these. Why? I forget why they did this. I think this is because of the way the video engine handles like monochrome versus 4-color modes. Oh yeah. Gosh. Oh fuck. Sorry. That's right. They have 9 bits instead of 8, and they use palette shifting to get that 9th bit. I think that's what's going on here. This chip is just fractal levels of weirdness. I love it. Gosh. Yeah, okay, so this is a very weird piece of code here. Now, I came to the manual to look for the instruction encoding. So distractible. There's this nice diagram somewhere. Oh yeah, there are very few special purpose registers. Because just generally, all the hardware is very simple. They just try to make things like uniform, and all the cogs are the same. The cogs don't have much hardware, but I did mention they have these counters and a video generator. So that's what most of these registers are for. So video configuration, video scale, phase, frequency, and there's 2 counters per cog, counter A and counter B. And then there's actually room for 64 bits of I/O, but the current chip only uses 32 bits. And the boot parameter. This is like how you can instantiate like computation processes on a different cog with a parameter. So you can give it a chunk of code to run, and that address controls which code is actually copied into that cog's local memory. But then the other parameter you can give it is just a 32-bit value that gets pasted into here. So you can use that directly. You can use it as a pointer to data in shared memory. Well, I guess this works too. I mean, I thought there was a diagram that was talking about the general structure of the instructions also. But so you have these special purpose instructions that do partial writes to only certain fields of a memory word. So you can use this to take an existing instruction and selectively overwrite, like in this case, the destination field or the source field or the instruction field. So here, for example, we're overwriting the instruction and effects field, setting the source field. So for example, if you have a move instruction somewhere else that has an indirect source with a particular address, you can overwrite that address with some value at runtime and then use that as an indirect memory load. So that's actually pretty common. Yeah, like instructions that pause until the I/O pins match or do not match a state. I wish these had a way of interrupting them. Like, I want to like these instructions, I really do, but every time I write a driver based on these, there's always a way to hang it because you can't get a core out of the state without the actual pin change you're waiting for. There's no like abort that you can send from a different cog. One workaround I've used is to just have a pin that I can include in the wait mask that I use as intercore signaling, but then you're stuck like using a pin for intercore communication, which is not ideal. $512 of Rainbow Tetris. That's interesting. I did not write that one. My 512 was a weird bootloader. It wasn't like a program itself, but it was a bootloader that was just, the idea was you want to get some binary into memory off of storage device and run it. It doesn't seem like that should be really complicated, but because of legacy PC architecture, there are actually a bunch of steps involved in that. So I made a bootloader that does, that. It switches the processor into 32-bit mode and loads a flat binary off of disk into memory and runs it for like a toy operating system project. Yeah, the thing that makes it complicated is that the storage access could end up requiring just like a lot of software, because I wanted this to be compatible with like USB flash sticks, for example, and like an entire USB stack and the storage driver, that's just big, right? But the BIOS is already reading that flash stick to get the boot record off. So the BIOS already has a driver, but the BIOS is 16-bit real mode code, and you want to be running 32-bit protected mode code, and you want to be able to access memory above 1 megabyte to actually load the binary into. So I wrote this tiny, awful bootloader that switches back and forth between processor modes a bunch to page individual chunks of the binary off of the storage device into upper memory by kind of bouncing them through low memory. But yeah, it's pretty weird. I guess I should probably show it since I've been talking about it so much. This is part of a weird little operating system project. Oh, is there now a new thing called Metal Kit because of Apple? Mine existed first. Look at that, 11 years ago. Yeah, so this is just like a little 32-bit toy operating system construction kit. I used it to make a bunch of weird little tests when I was trying to understand virtual machines better and make tools for developing stuff at VMware. Oh yeah, somebody else sent me a patch. Thank you for sending me a patch. Merge from SVN to Git. Wow. So yeah, this was for stuff like, I don't know, here's like a palette swapping or palette animation demo or something. So you could have timer interrupts, and you could do sine and cosine. Like, you could do floating point math in an interrupt. Look at that. That actually worked. It was supposed to work even. And then you could make calls back into the Visa BIOS to do like high resolution graphics. This was fun at the time. So yeah, this is just like writing code for like x86 PCs kind of at the same level of abstraction that you would usually be writing code for like an Arduino or something. It's like a low-level library for doing the boot up and for accessing some of the hardware. It had like keyboard and serial port and graphics drivers, mouse drivers, stuff like that. Oh gosh, this was also weird. This code was also weird. Yeah, so this was all 32-bit code, but I had this whole system for re-entering 16-bit BIOS routines at runtime in order to do graphics and whatever. ASM volatile, good times. Oh, look at that. We'll just do write to CR0 right here. Oh gosh, stupid x86 tricks, right? I still find some of this stuff amusing, but I don't know if I'd ever write code like this again. This is the piece I was actually coming here for. So yeah, this thing fits in 512 bytes, and it is a boot sector, so it has partition tables in it, but it's also executable code that loads another binary. So this was designed to have some information accessible via linker variables. So I actually had a linker script that would calculate the partition table values, and then this assembly file would import those. So yeah, this is the 16-bit entry point, and that sets the segment to the correct segment value, and then jumps down here. And then we like initialize the registers and the stack and make sure the interrupts are very off. And we save the disk drive ID. And then there's this unspeakable horror that if anybody, I don't know, if anybody just wants a good anecdote for how legacy filled the PC is, go research the A20 gate. A lot of modern BIOSes will not strictly require this, but it's easy to do and it's necessary for compatibility on older BIOSes. It has support for both LBA and CHS disk addressing because some floppy drivers don't like LBA. So yeah, you could boot off of a floppy disk or a USB stick or hard disk or like a virtual hard disk. Anything the BIOS could handle. Disable protected mode. Printing characters using the BIOS. This just keeps going back and forth between 16-bit and 32-bit. Oh yeah, we're setting up the GDT. There's the actual main. So then from this point on, it can all just be normal C code, just normal 32-bit C code that doesn't have to be written in inline assembly everywhere. Oh gosh, yeah, the EFI source code, I dealt with that a little bit when I worked at VMware, and that was certainly hard to read, but for different reasons. EFI source code reminds me a lot of early Windows source code. I feel like maybe it has some of the same influences. Like, EFI is kind of like if they took... I didn't realize Jarrett was talking. I should have put my headphones on. Didn't mean to be talking over you.
Hey. Hello?
Hello. Does this work?
Yeah, now I can hear myself on the stream.
Cool. Welcome to the stream. Oh yeah, that's how much we would copy at a time. That's great. Okay. Stupid x86 tricks. Stupid propeller tricks. Yeah, so this assembly language is kind of strange and kind of confusing maybe if you're used to other architectures, which I mean, I don't know who would be used to this architecture. But this is like destination comma source. This colon here indicates a label, like an address the uh, in the cogs memory. So it's going to be the offset of. All right, Jarrett. If you're not talking, could you mute the microphone because we can hear your keyboard. Um,
Oh, sorry.
no
I
worries.
meant it's actually a sewing machine.
Oh, nice. Is your sewing machine not crashing? So yeah, here we're reading. So this PC actually is the sort of virtual program counter for
My sewing
this.
machine is not crashing. It is entirely mechanical.
That's good. Fewer moving parts. Oh gosh. Hey Tuco, I guess Tuco really wants in. I don't know if I should let him in. All right. Maybe we should just jump into the code or the hardware here. Enough time staring at the computer. Tuco. Tuco sure wants attention. Alright, so I've got this pretty beefy power supply running the whole thing. Pretty overkill, 30 amps, 12 volts. It's unfortunately a little bit noisy. Let's lock the focus. Just got a satisfying clunk switch and then kind of makes this happy beep when it turns on. Yeah, an actual sewing machine. I'm done going over the code for now. I don't know how much patience anyone's got for esoteric assembly language tricks at this point. Oh, Tuco. So yeah, it looks kind of like that when it starts up. Let's get a closer view of the screen. I don't know if I've ever had this on a stream, the sewing machine. For a long time, this was actually not in my possession. I actually gave it away to a friend on Twitter at the time, and so it was at her place for a long time. And then eventually, I think she was moving or something and wanted to give it back to me. That's when I got it back without the pedal. And then I found that Adafruit pedal that I could make into a close enough match. Tuco. All right, so power on. Tuco. Tuco, what do you want? He's not gonna leave me alone. I should see what he wants at least. Oops. Wi-Fi camera. Gosh, Tuco. I think the Wi-Fi camera's off. Just a moment. Tuco, what do you want? Hey. Hey, Fuzzboy. Do you need anything? Do you want the door? I guess we could use some fresh air. It's kind of stuffy and warm in here. Tuco. Of course the battery on the Wi-Fi camera died. Hey, Tuke. Tuco. Can I give you some kind of view here? Press the red button. Oh, Tuke. Hey. Oh, it's the green button. Tuco! Gosh, Tuco. What? You just want pets? Hey! You want more attention. What does this cat want? I think the fan turned off. I might want to put... The fan in this house was wired into a timer, which is kind of weird. I can't just turn it on and turn it off. Put some more time on the fan. Oh, Tuco's just melting onto my shoulder. Tuco, are you lonely? Oh, gosh.
So your house has like a giant fan for pulling air through it?
Oh, I can't quite hear from my headphones. Maybe I will turn the speakers on. Can I reach the speakers? How does that sound? Yeah, I think I can hear that without causing too much feedback. Tuco. I know there's a huge delay on the video. This is coming from a camera that is not real time, really. It's not a terrible Tuco cam while the other one is out of battery. I guess I should turn on the big fan. Yeah, all the equipment in that room is running a little hot right now.
Oh, does your house have a giant, terrifying fan that pulls air through it?
Whew. Just sucking all the warm air out of the studio. I mean, it's not that much colder outside, but it's definitely colder outside. Yeah. Maybe that also kind of gives you a sense of the scale. It's a little bit crowded in here, but there's some room kind of near where that whiteboard is that probably be easier to use once I put some shelving on the wall and put the whiteboard up. The surprising thing is that the giant fan doesn't have home automation. I mean, yeah, I haven't really gotten to that point with this place yet. There's still a lot of work to do. I mean, it just needs basic electrical work still, so I'm not really getting fancy with it at this point. Aw, Tuco's great. Hmm. Oh, Tuco, are you coming over here now?
Is Tuco a very schedule-oriented boy?
Yeah. Certainly seems to be lately. Like, he's been getting up at like 5 a.m. every day, and then he, like, kind of is chill and, like, sleeps and, like, explores. And then he gets really active in the evenings.
Yeah,
But he
one
gets pretty
cat.
antsy if he can't be around me for a while.
Oh,
He
for
seems to be
sure.
more annoyed if I'm here and not letting him hang out than if I'm just not here.
Yeah, our one cat is he's obsessed with schedules, and he will manage the hell out of us and require us to go down and eat at specific times, go to bed at specific times.
Oh, wow. Yeah, Tuco doesn't usually get me into bed, but he certainly gets me out of bed. So, yeah, I've got this whole, like, encoder UI thing. It has a menu option that just does a stitch. Right now the bobbin winder's on, but if the bobbin winder isn't on, whoops, it crashes. So it does crash. Let's reboot it. Oop. I think it was at a weird spot in the cycle. It's working properly at that point. So it'll do stuff like that, which I thought was useful for certain weird kind of embroidery things. Has some modes where, well, so the default here was servo mode. So if I just actually squeeze the foot pedal, you can see it runs pretty smoothly at low speeds. It's a little jerky here. I think that's actually some gunk in the mechanism. I think the control loop is oscillating a little bit because the mechanism isn't running super smoothly. But up at that speed, it's pretty even.
Yeah, I'm currently doing a sewing project where this exact thing would be so useful to me, which is kind
Oh.
of why I'm like watching this. I'm like, huh, I don't know if I could do this because
Well,
the default motor in the machine, I think it's an induction motor, right? Which is
mhm.
not super easy to do speed control on without a VFD, right?
Yeah, exactly. I mean, I tried just making a triac speed controller, and it was not nearly good enough, and I didn't really want to go into VFDs for that. Yeah, I don't even know how well a VFD would have worked on that motor because it just seemed like, it just like wasn't mechanically great at the kind of high torque, low speed range. So I don't know. Can I get the screen on here too, maybe? Hey, Took. Yeah, the walking Kirby was an important part, right? Yeah, I think that was something I had sitting around from like a sprite library test that I wrote for this LCD driver that I also ended up writing for the project. So this is one of those projects where I ended up just creating a bunch of additional work for myself by, having sub projects that needed doing. Oh yeah, so this one's also fun. You can just press the pedal, and when you press it, the needle goes down. When you release the pedal, the needle goes up. Kind of weird. There's another mode where it acts like servo mode, except it'll always stop with the needle in the down position. This one's a little bit scary because sometimes it can do an extra stitch that you're not expecting. Like that. But if you're doing mostly like long stitches that don't need to be super precise and you want to make sure that the needle stays like in the same hole as you change directions, I found this kind of useful. And there's an analog that always stops with the needle up. Again, kind of with the scary extra stitch. That's something we can fix in software. Ooh, what just happened there? Something's oscillating. I've never seen it do that before. I think I might need to recalibrate the sensor. Because if it doesn't stop in the place that it thinks it's supposed to stop, if it like overshoots it, then it'll end up kind of doing another stitch to get back to that stopping point. And so yeah, that might be a sensor calibration issue. Because this has been sitting around for a while. It's just concerningly fast though, like that needs changing. Okay, so then open loop is just the pedal controls the amount of power the motor gets. So for a while I can kind of squeeze it and nothing happens, and it starts kind of suddenly. And I can carefully try to kind of run it slower if I'm really light on the pedal. But at high speeds it behaves a lot like the servo mode because there isn't as much like drag. Has a decent amount of power though. Alright. So that's pretty much all this does. It just has another motor and a couple of modes, but like the main reason I wanted this is so that I could have the sort of smooth speed control, which is just this default mode. Which is not even quite as smooth as it was supposed to be because there's probably some gunk in the mechanism, but it doesn't do that thing where it just buzzes and doesn't move anywhere like the other motor. So it's a pretty strange device. So far it hasn't been crashing a bunch. It seems to vary, like we saw it crash once, but it's been behaving itself quite well for this demo so far. We can also run it with the bobbin winder, which just kind of connects the motor to this post on the top without most of the sewing machine mechanism going. Oh, there it crashed. I think it crashes a little more readily with the bobbin winder only because I think the source of the noise is induced voltage and current in the motor. And so I think when there's less of a load on the motor and the motor spins faster, I think the extra velocity increases the amplitude of the noise and makes it more likely to crash. So in this case, the software is still running, but the LCD crashed. I don't know whether it's the LCD cog on the propeller or the LCD driver chip or something in the LCD crashed, but now the propeller crashed and it's stuck at the same speed. So actually, only some of the cores in the propeller are crashing. Um, I think the LCD driver core must have crashed, and the core that handles user input from the pedal. So the core that's actually in software turning the motor on and off to modulate the pulse width modulation, like that core is still running. Because of course everything is written in software. It's a propeller. It's of course it's doing the PWM in assembly language. um, which is actually kind of nice because I can do things like somewhat intelligently limit the minimum pulse period, which is required for this motor driver. So it's not entirely bad, but it is very weird. So, I thought I actually had one of these buttons wired up as a reset, but last time I was having trouble getting that to work, so I've just been power cycling this. Yeah, now it's crashing fairly easily. Yeah, now the same state where it's just stuck running. So, that's enough of a demo of the problem. I'm going to get the O-scope on here and we can take a look at some of the electrical environment that's going on. Oh, I need to get have another brief restroom and water break. I'll be right back. Maybe I can get this camera on Tuco, because he seems to be interested in that area. Alright. Maybe he'll hang out there for a bit. It's important to stay hydrated. Hey, Tsuko. Oh, that's a good question. Is there a reason I'm fixing the sewing machine? Mostly I wanted to make some face masks. I mean, it's something that I've wanted to fix for a while, but that's the immediate need. Like, I think I have enough cloth and sewing supplies to kind of cobble something together, even if I don't have, like, the exact recommended materials. And it'll beat, like, clipping random pieces of cloth to my face. Tuco. Okay. Oh, Scope Town. Let's take advantage of this great view of Tuco while we have it. I mean, I know he's just, like, cleaning himself, but, I mean, he's a great cat, right? Like, who can argue with that? Covering more and more of the wires. Oh, Tuco, are you gonna jump somewhere you shouldn't? Tuco, please don't. Would it be a bad idea to play Automaton on the stream, or the worst idea to play Automaton on the stream? I wonder if it would scare Tuco away. Tuco, are you trying to chomp wires? Okay. I think I wanted to just start out with monitoring the input. Oh, there's my wires. We require additional banana leads. Oh. Automat. Oh, it's just an instrument I've been trying to learn. Yeah. Not gonna bother with that, actually. I was thinking that I could find a banana plug in there to use as something to grab the oscilloscope lead onto, but I don't have any plain banana plugs, and I don't want to hang a long extra cable off of this thing if I'm trying to measure it at all. I don't see a great way to get a connection to it otherwise. I mean, I'm going to open up this motor control box pretty soon, but I wanted to at least measure it before doing that. Oh, this will be good enough. Just use one of these. This makes me nervous having banana cables attached directly to, like, anything attached directly to a 12 amp, or sorry, a 12 volt 30 amp power supply. This is, oh gosh, is this not even, I think I can just take these plugs off and use them. Yeah, I agree with Laura's comment that automaton might be a great ground for a sort of DIY instrument design. Yeah, I've been even just having fun with just using the line out and filtering it to sound a lot different. I think I've got a filter loaded right now that's got like a bit more of like a string instrument vibe to it. Yeah, I mean, it'd be interesting to open up the automaton and look at the like what the oscillator in there looks like. Like if you look at the audio waveform, it's like a impulse train. It's just a train of negative impulses that are all pretty short, kind of a consistent width, and then the pitch changes the spacing of the impulses. So it's like a small duty cycle square wave generator. The duty cycle changes with pitch a little bit because it seems to be constant on time and variable off time. It's also just clearly an analog circuit with a bunch of weirdness to it because, you know, the amplitude and the DC bias kind of shift a bit depending on what pitch it's playing, and there's a bit of a settling that happens when the pitch or when you first do a note, like first press a note in, like it kind of takes a sec to actually settle to the right frequency. Depending on the power source. It does that less when it's running off of a 5 volt USB adapter, but running off of weak nickel metal hydride batteries, it actually kind of has a very soft pitch that kind of takes a while to settle. Yeah, so those videos I think are the ones that I know about, but I think are bad. Like I mean, you can watch them if you want. I just don't want to watch them right now. They are filmed on a low resolution camera, and they don't really, I don't know, they just don't really explain the project very well. They just kind of are like, here it is, it's running, you know. It's like minimum viable electronics show and tell video. Oh. Always with the scaler. Half want to open up that scaler to try to figure out how to change its default, so I don't always have to press that VGA button every time I turn it on. I don't know how I feel about this black void that the O-scope and the DSLR are existing in. I used to do this like weird layering effect on the DSLR back when the DSLR had all this on-screen display stuff I couldn't turn off. Gosh, this camera is getting kind of warm. I'm worried that it's gonna get cranky even if I'm not recording in 4K. I might have to turn on the air conditioner. That's funny. I'm actually alright with this temperature personally, but maybe the equipment is starting to get unhappy. Okay, so let's just look at the power. Let's see, not even internally, just like what noise is escaping out onto the input supply, because that'll give us just like a really rough idea of how much noise might be making it from the motor controller through the DC power supply and then back into the microcontroller. So this was the first thing I tried. Let's turn this power on. Now we've got our 12 volts, and we're probably going to want to put this in AC coupling and zoom in, but I'm going to leave that on DC for the moment. So you could already see a bit of a flicker there, like something had a pretty serious inrush there. There's really no inrush limiting here. Then I'm going to squeeze the pedal. So you can already see, okay, so it's already crashed. So I'm just going to leave it in this crashed state with a constant low speed. And try to trigger on this mess that we're seeing on the power rails. So that's like usually 5 volts with some like maybe slightly higher peaks that are harder to catch. That's a lot of noise. 5 volts riding on 12 volts. So, I mean, we can assume that probably a bunch of that is making its way back through the power supply or onto the ground, most likely. Let's go to AC. Oops, that was just triggering. DC triggering is much easier to adjust. So these seem to just correspond with the pulses where we're turning the motor on or off, probably. So let's also maybe get the 3.3 volt power now. Actually, I'm slightly worried that we might get misleading results if we have multiple oscilloscope probes that are connected to ground that are supposed to be the same but actually aren't. So it might be a little more reliable to measure these separately. This whole thing is super awkward to work on. I think that's on the 3v3 rail. Oh. Okay. That seems pretty stable, actually. Let's get a closer look. Well, there's our pulse. But the amplitude, I mean, that's like peak to peak, a little over 200 millivolts. And, I mean, that's not great. It's not as bad as I thought it was going to be, but it's like we could probably use some additional capacitance there. But there's probably a better place to focus. Yeah, I think that looked much worse when I had the ground between that and the input coupled. Because I think a lot of our noise is probably happening in the ground side of the circuit. Okay, and so it's already crashed. Okay, I think we want to try to get access to the... probably just like all three of these motor drive signals. What is going on here? Oh, TFL is thermal flag. Yeah, the motor driver has over temperature detection, but I don't think I ended up implementing anything with that. Maybe it just checks that, but I don't remember that being useful. Because the driver runs pretty cool on this usually. But it has PWM, brake, and direction. So yeah, I don't know if I even wired up the thermal flag. I just want to poke around these resistors. Oops. So I added these 100K resistors in series with all those inputs. I didn't add like a capacitor. That would have helped. Like a resistor and a capacitor would have been an effective filter. Just the resistor was kind of just like rolling the dice. So like one thing we might try is to, I think I calculated that if we were keeping those 100K resistors, then it might be reasonable to add a capacitor in the neighborhood of like 100 nanofarads. No, 10 nanofarads. 0.01 mic. But my capacitors are a mess, so we'd have to search for something. Maybe this would be a good time to go back to the overhead camera and get this camera out of the way also. Oh, it is running warm. Yeah. No, I think we can find some parts, but yeah, I mean, I could certainly change the resistors. I might want to change the resistors anyway. I might also want to add a buffer chip on the assumption that the buffer can probably handle some noise that the microcontroller maybe couldn't. But yeah, I'm pretty sure I could find the right resistors and capacitors. I'm less certain I could find like a logic buffer chip. I mean, I'm sure I have them. It would just take longer to find and be annoying. I've got this snake of wires here where like I've got to hang the SDI converter and the power supply for my camera off of just anything nearby and then drape the wires down. Gosh, this camera's already worryingly warm. Maybe I will turn on the air conditioner. Oh, I'd have to move Tuco, because I don't want to run the air conditioner with the door open. Hey, Tuke, can we move you gently? It's okay. Oh, there's so much time on this timer. There's a switch that makes the fan go much, much slower, which is something. I wonder if there's a way to convince this mechanical timer to turn off without breaking it. This is the kind where it feels like if I just force it to turn in the wrong direction, it just slips. That's super annoying. Tuco's laying somewhere cool. Oh, is this working? Huh, can't tell if the air conditioner's working. It seemed like it might have turned on really briefly and then turned off. Excuse me. I wonder if I tripped a circuit breaker by trying to power this up at the same time as the fan. I thought the air conditioner had its own circuit. Did the air conditioner choose right now to break? Huh. This is great. Oh, well, I should at least let the camera cool off, probably. Maybe I'll take a voltmeter to the thermostat before actually trying to check the breakers or climb onto the roof, which are the other options I can think of. Ugh. Hi. Oh, this thermostat is terrible. I need to replace it with something. I haven't decided what. Oh, are these wires labeled? I think there's a standard color code, but... we have 27 volts AC, which seems normal, I guess. I've never probed at this before. Maybe the thermostat is broken. Or maybe it's the compressor. You know, if the thermostat was working, it seems like I shouldn't be getting voltage across the cooling circuit. Maybe that's the problem. I should look up what these wires are for before I start shorting them together. Thermostat breaks on stream. Yeah, I don't even think I need a thermostat manual at this point. I think I just need to know what the wiring color code is. I mean, it looks like it's just like a relay closure 24 volt AC circuit, but I just want to make sure before shorting stuff together. Oh. That's the AC starting. Maybe the thermostat had some kind of like hysteresis lockout thing that got triggered accidentally. Okay, well it's on now. Yeah, I guess I should read my thermostat manual. Maybe I should put the cover back on too. Hopefully that won't break it. I definitely need to replace the timer that fan is connected to. It's annoying that I can only run it slowly and not turn it off right now. What else is on this circuit? Could I just turn off the breaker that the fan is on? The timer won't count down though, it'll just delay the problem to later. Same circuit, living room lights. Yeah, I'm just gonna leave it on. That's not optimal. Well, hopefully this will cool off all the electronics in here and my camera won't overheat and we can get on with the streaming. Using the power of air conditioning. The air conditioner definitely shows up on my voltage monitoring for the house. Yeah, it looked like that was going on. It looked like they had just like a power input and then wires that you would short for heat and for cool. But yeah, it looks like this was entirely something that happened inside the thermostat and was probably semi-intentional, I guess. Oh, that's much better. Man, air conditioning is nice. It feels like such a luxury though. Like I don't like using that much energy, but you know, sometimes it's necessary if you're doing a bunch of equipment, I guess, and you don't live in a super cold climate. Gosh, liquids on the green screen always look pretty fun. Okay. Is the camera gonna behave then? Gosh, this needs more hold. I'm using this arm with a tube that's narrower diameter than it's really designed for. Sure. All right. I had a diagram handy and then I moved it. Okay. I want to satisfy my curiosity about whether that thermal flag pin is actually connected. I'm just going to try probing at it. That is... Oh, what is even going on? I'm probably going to have to look at the other side of this circuit board. Because, yeah, actually this is not what I thought it was. Alright, fine. Let's flip it over and actually look at the wiring. Because I can't tell what's going on in this mess just looking at the top side of the circuit board. This electrical tape is all dried out and gross now. Okay, so this coax is for the phototransistor. Direction does matter. Looks like I had a flat side on here. Oh, I see. I marked... This is one of those connectors where there's an asymmetry where one side is thicker than the other, and so I marked the thick side with a thick Sharpie line. Which is not great, but sure. And then... This is also charming. I think I didn't have the right size connector, so I used one that was actually too long. So you actually have to line that up with just the top side of that connector. It's another hazard built in. And then, do I have to take those off? I don't think I have to take those wires off. But yeah, so that was like that. Oh, these are just wood screws. Thanks, past me. Great prototype. I mean, this piece of wood that it's screwed into is like a piece of old furniture. Like I didn't really do any shopping for this project. I just used stuff I already had. Yeah, I kind of like engineering sometimes that's more like an episode of like a Junkyard Wars kind of show than like, you know, the kind of engineering where you spend 90% of your time like just ordering parts and like specifying like what supply chain you want to interface with. It's the supply chain of I already had this somewhere. Good luck finding another one. These standoffs aren't even glued down. Okay. Okay, I don't see anything connected to the thermal flag pin, so I think my vague memory that I left that off is probably correct. It'd be cool if I had a correct and up-to-date schematic for this thing, but it's way too prototypey for that. Like, there will never be another one of these. Like, if I were developing this into, like, a kit or something, then it would be based on probably significantly different parts at this point. I got the computer screen on here too, so you can follow along with this diagram maybe. Man, the LED in that first button on my switcher is going again. I wonder why I've had two LEDs with the same problem in a row. Like, it seems like it might be like a cold solder joint elsewhere at this point. I should really be doing this in studio mode so you don't have to be watching me fuss around with the OBS, but here we are. I thought you could alt drag these handles to do a crop, but that seems to be failing. Oh, Tuco. Tuco, hey. Honey boy. I think Tuco and I are both a fan of the slightly warmer weather here. He seems to be kind of a jungle cat at heart.
How warm is it there right now?
That's a good question. I think it's probably in the mid 80s outside. Like, I don't forget what that is in real units. It's actually really nice just standing around outside, but like this room with the equipment and the underventilated nature was getting a little toasty. Oh, am I gonna have to look up how to do this in OBS again? There might be some other reason it's not working. Should be alt. That's weird. Alright. We'll just do this the easy way. Alright. That'll just have to do. Oh, Tuco's right over there, sitting in a cable zone, making me nervous. Okay, so pin 1 is over here. We are interested in the kind of opposite side or opposite corner of the chip where pins 21 through 27 are. So that's over here. So this unconnected pin is the thermal flag. Then we have PWM. So these three all have series resistors, it looks like. I only see 2 series resistors on the top side. I think I also disconnected the direction pin because there's no reason the software should be telling this to run backwards. So yeah, I don't think I actually wired up direction. And brake and PWM are going through these 2 series resistors. What are those?
It's funny you mentioned never going backwards because I'm working with some fabric right now that is it's really difficult to work with. It's like really thick fleece, and I'm sewing through 2 layers of it, and I can't even use the pedal because it skips stitches constantly.
Oh no.
So I have to like push it down through the fabric and then back it up a little bit and then continue on. So I've just been sewing the whole thing on the sewing machine, but just by hand with the wheel.
Oh yeah, wow.
So that would be so nice to have it do that for me.
Gosh, yeah. I forget if there's some mechanical reason I actually took out the direction pin. I mean, this sewing machine has a mechanical reverser pedal, so you can, with the motor running the same direction, you can push the thing and it backstitches. But yeah, I don't know if there might be also a reason to have the motor actually go in reverse. I think at the time, I mean, I definitely left room for the direction pin in the design. I forget why I took it out. Like, I forget whether it was something where I just didn't want to write the software to, like, I didn't want to, like, spend the extra cycles to have a bidirectional motor controller in the code, or whether it was something I was doing to remove potential sources of noise coming back into the MCU. So it looks like thermal flag and direction are just open. And then interrupt. Oh, that's the interrupter, right. So that photo interrupter, and then PED is pedal, and then tachometer is the output from that comparator. So those are all just going to be weird point-to-point wiring. Hey Tuco, what are you doing? Don't shoot! Don't bite any of that, honey. Don't bite any of that. Oh, Tuco. Oh, Tuke. Several of these were reworks. Like, I think that inductor is for a new LC filter I tried to add. I don't know where the C is that goes with that. Oh, that's another good point. Yeah, the always stop down mode, those could definitely be implemented better if it could go backwards. Yeah. Yeah, I vaguely remember there being some mechanical reason why it didn't like running backwards from the motor drive side, but I don't remember if that's actually the case. This tiny little capacitor. I think that's for the reset circuit.
Yeah, typically because like that reverse button or lever, it still runs the needle mechanism forwards. It just reverses the feed dogs. So if you like turn the wheel backwards, it really does not like that.
Yeah, that's true. Oh, this is super awkward. Yeah, so this orange wire here, I should get my pointing tweezers. That's the tachometer signal coming from, I assume that's from the comparator. There's that series. I think that is a 270 ohm resistor. Why did I use a 270 for that? Whatever. It's probably not causing that much harm. So the pedal circuit is right there. I think that was just a couple of resistors. Yeah. It does like a software analog to digital converter to read the pedal. Yeah, and that's that 0.1 capacitor. Yeah. Oh, I think we know what to probe now. These standoffs are all going to get lost if I don't put them aside. Oh, Tuco is going to want to play with the standoffs. Delicate and messy. I mean, it wouldn't be huge project at all to just make a printed circuit board for this if we wanted to tidy up the design. It's just always hard to know how much time to spend on any particular like renovation project. Oh, Tuco! Tuco's crawling behind the green screen. I guess I should be less worried about that because it's zip tied down, but where do we even get ground? I've been clipping onto this capacitor leg for ground. It really gets in the way though. Yeah, another mistake. You should always add extra ground posts to your circuits to make it easier to hook probes onto them. Oh gosh, that lead is like really corroded and gross too. I mean, I was trying to use a different one than the one I was just using to get more access. There's just a thing I can clip onto over here on the back side of the board. Kinda. Yeah. Yeah, right. One can never have too much ground. Alright, so which one's which here? PWM and then brake. I forget what I use brake for even. Like, I think I'm probably only using the brake pin in, like, exceptional circumstances. Maybe it's actually worth reading the motor driver to see what I'm even doing. We're going back into weird assembly language land, but not the LCD driver, because we don't care about the LCD driver right now. The LCD driver is super complicated, and I don't feel like going into it right now. If anybody really wants to know about the LCD driver, maybe we can take a tangent at some point with proper preparation. Like caving gear or something. Why is this not loading my submodules? I don't know why modules are not showing up below that, but for some reason they do on these other source files, but not main.spin. I don't know what's going on there. It's supposed to load the code for all these objects I'm referencing. Tuco is still behind the green screen. This is, so I have like the main function, or the main sort of top level module that supports all the UI stuff, but I've also got some very simple alternative modules that I used during development that have like serial port debugging and just do one thing as like a test harness for the other modules. So I actually have this module called Sewing Machine that just implements like the top level kind of stuff in the sewing machine that isn't user interface. So it can do things like read the pedal or turn on the sewing machine or move it at a particular speed. And it just has these top level kind of entry points that switch it to a particular motion control mode. So then I guess this doesn't have any submodules. These, yeah, that's correct. These processors don't have interrupts. They have a bunch of other functionality that you can use to implement functionality that's like you would you normally get from interrupts. Like they have like these event-based timers. Excuse me. They have these like event-based timers where if you want to send out pulses at a very regular interval, for example, you can just read like a 32-bit tick, like a clock cycle counter from the processor, do some arithmetic on it, and then wait for another particular timestamp to appear. So that's actually really useful. Like you can just calculate intervals and like wait for them and have cycle accurate wake ups on the particular processor. That's kind of the usual way to do timing of intervals that are longer than what you would just cycle count by hand. So you can do timers that way for like external events. Like actually that's what this is right here. This wait PEQ is waking up a processor when the external pedal pin reaches a particular state. So in this case, it's waiting until it's low. So the value it's waiting for is 0, and then this is the mask of pins that it's looking at. And this is an operator that is like 1 bit shift. So it converts a bit number into a mask for that bit number. This language has a few like weird special purpose operators like that, but a lot of it kind of is reminiscent of like C or Pascal or JavaScript. So yeah, the pedal actually, I don't have like a separate process handling the pedal I/O. The pedal is just something that blocks whatever thread calls this read pedal routine. So you can call read pedal from like your main spin level source code, and that'll just kind of drill down through here into the raw read pedal, which charges the capacitor, and then waits for what is that, a millisecond, and then starts discharging the capacitor, saves a timestamp. So CNT is a register, like a special purpose register that has a global cycle count for this processor. I'm saying for this processor, the register exists per core, but I think it's guaranteed that they always stay synchronized between cores. So you can use them for like, you can like ask other processes to rendezvous at a particular timestamp, which is kind of useful if you're trying to spread cycle accurate I/O across multiple cores. So that was a trick that I ended up using for the USB host. I could have 2 cores both wait for calculated timestamps, and then after that calculated timestamp, they would start sampling data from the USB RX pins just as fast as they can, or D plus D minus. And because I actually had to sample like one, what was I doing? I think it was something where I had to do these bursts of I/O where there wasn't actually enough time to save the data to memory if I was doing it all in one core, but if I had 2 cores interleaved, then I had enough time to write the data back to memory, or something like that. Yeah. Such a playground for weird assembly language tricks, this processor is. But this isn't even assembly language, right? So like this is a little bit more like the code that you would write for something like a basic stamp or something, where you're doing like timing IOs, like waiting for capacitors to charge or whatever. Like this is kind of what Parallax had in mind when they were designing the spin language, is you can do a lot of the same sorts of things that you would do in like a basic stamp kind of environment where it's like you have a fairly high level, fairly slow interpreted language that gives you little primitives that let you do fairly fine-grained IO operations. And then by having this global timestamp counter that you can wait for, that kind of lets you extend that even further, where you can write this relatively slow interpreted code that can still produce fairly accurate waveforms as long as there's enough time to run the instructions. You can still align your IOs just like clock cycle accurate, even if the code that you're running is like hundreds of clock cycles per statement. TPU and Motorola's processors. I've never used those, but I think I heard someone else make that comparison too. But yeah, I'm not familiar with that architecture. The architecture I know of that's most similar to the Parallax propeller is the XMOS. I forget who makes that. I think they're just like their own company. But it's also a multi-core microcontroller. Whereas Propeller goes for simplicity and like easy to learn, easy to teach. Like the Propeller, you can just like look at the instruction set table, look at the memory map, and just kind of understand it in an afternoon if you want to. Whereas like the XMOS it has like standard libraries and compilers and like pages and pages of registers and much more advanced hardware multi-threading. Whereas the propeller is like kind of more like a retro computing system where you're dealing with very limited amounts of memory and um, kind of limited amounts of complexity, and you have kind of a simple and elegant split between the hardware and the software that at the same time gives you like kind of a weird set of constraints. Whereas the XMOS kind of goes more in the like professional industrial end, where like they don't want to give people weird constraints. They want to give people just a really powerful general purpose platform. But the way that comes off is that, oh, now you need like 8 power supplies, and you have all these complicated development tools, and there's not like a one-to-one mapping between hardware threads and hardware processors, and there's like a scheduler built into the silicon, and so that's a bit more of a complicated system, and I don't think it gives you quite the like cycle level deterministic accuracy that you get in the propeller. So I'm not as familiar with XMOS. I think I like played with their development kit a little bit, but I haven't done anything really serious with them. But if I remember what they're doing correctly, um, it's all based on very fast but not instantaneous context switches. So you can have like a one cycle or a couple of cycles switch between hardware threads, um, but they're not necessarily running at the same time. But then they give you these really powerful I/O and communication primitives between processors and between processors and the outside world. So you can do things like implement USB to, I think even USB 3 nowadays in software on one of these processors. Um, it's like designed to be great at real-time audio processing and just funneling data in and out of a whole bunch of I2S channels, and so it has these fairly fun configurable shift register modules. So whereas the propeller has like one special purpose kind of outgoing shift register that will just like send out bits without the processor having to pay attention 100% of the time, it has one of those that's designed for video, but you can repurpose it for a bunch of other stuff. But that's like how the kind of example code for the propeller that does video output, like all of that uses this facility, in its intended purpose. But the propeller doesn't have something equivalent for input. So when I was doing that USB controller hack, the sort of bit-banged USB host controller, I could use that video generator engine to do the output side, but for input I had to do something much weirder, and that was when I was like interleaving multiple processors, because I did have to just read the port over and over and over again. But yeah, I kind of like this. Just it's gives you like a lot of the same fun of a multi-core platform, like a modern computer or like XMOS or whatever, but in this context where it's intentionally designed to be simple enough that you can just understand it or teach it in a reasonable amount of time without it just being this very open-ended stack of abstractions. This is that beep that we were hearing when it turns on. So it stops the motor and then just pulses the PWM. So here we're using the brake to stop the motor. That doesn't seem strictly necessary, but I guess it's a nice touch. But, I don't think that's really important. Actually, that's not even pulsing it, right? That's just setting it into a known state. Gosh, I always forget what these are. I might have to look up the polarity for like, I always forget like oops. Something drag and drop triggered the accessibility firewall. That's funny. Oh, they have a built-in manual here. That's handy. Oh yeah, high is output, low is input. And then the other thing I forget is these silly tilde operators. So it has these unary operators that, so there's sign extend if it's a prefix operator, and post clear or post set if it's a postfix operator. They went a little overboard with the operators in this language, but it gets fun. It's just that it's easy to write somewhat obscure code. And not just that, but because so this is a language that is again very very simple. It doesn't have an optimizing compiler. So the code that you write is basically the code that gets stored into memory, and then the interpreter runs it. It's not like the text of this, but it gets like tokenized and very lightly parsed. I think it knows how to do basic constant folding, but it doesn't even guarantee that it'll constant fold. Like there's an operator that lets you force it to constant fold. So you can say this expression must be evaluated as a constant at compile time. Um, but yeah, I think if you just generally start making expressions in spin that are not necessarily, that aren't like annotated as constants, but could be constants, the compiler isn't guaranteed to figure it out. In a lot of cases, it won't. It's basically a tokenizer rather than like a full compiler. So again, not like optimal for software development, but really nice for having an easy to understand and easy to teach system. Would have been a more powerful teaching tool, in my opinion, if they made this the language tools open source from the beginning, or like talked more about the way that was tokenized and stored. I think in the earlier part of the product lifecycle, they were trying to be really secretive around some of that for unclear reasons. I think they were worried about losing control of the tool ecosystem, but then, like, of course, people make their own tools, and then it turns out some of them are really good, and so, now there's just a bunch of different tools you can use to build code for this chip, and they're all a little bit weird in their own way. In fact, this isn't even the original propeller tool. The original tool was Windows only, and I think Parallax has always been in the habit of writing code that is not super portable. So like the old basic stamp tools, they had a DOS version, and for a long time the only thing you could run it on was DOS. They eventually wrote a Windows version, but like the Windows code is like, it looks very Windowsy. Like it all uses like native Windows UI features, except for where they decided to just like have crazy colors and crazy fonts because they're Parallax. And then they tend to like these like nice portable like single Windows binary kind of things, which are nice, but it also, they just don't have a workflow for porting a lot of this stuff. So this is actually a rewrite. This Propeller IDE thing, I think it's basically official now, but it started off as just a third party. I don't even remember whether it was originally open source. I'm pretty sure it's open source now, but it was just like a third party IDE that they eventually kind of adopted as a more official thing. And now it's like the only way to run it on Mac if you don't want to run it in a virtual machine, which is what I used to do. It supports all the box drawing characters and stuff. So like the same weird font that's in ROM is also, of course, in the IDE. So you can just type characters and have circuit diagrams and stuff, and then display those on the television that you plugged into the microcontroller if you want to. So a lot of this is just the high-level spin code. So this usage of the break doesn't really matter. So we're doing... So 2 tildes is post set, 1 tilde is post clear. This is like one of those things that becomes second nature if you're used to reading propeller code, but it's easy to just remember wrong if you're not used to it, because it's very arbitrary. So in this case, this is just setting these pins as outputs, and this is turning them off. So by turning them off before setting them as output, we're making sure that we don't like inadvertently drive them high if they weren't already being driven high, if they were like floating. So we set the output register, and just like a lot of microcontrollers, there are separate registers for output, direction, and input for each I/O pin. And so direction isn't even being used, so like that code doesn't matter. And we're just using that timer. So this is actually a pretty classic example of you can just use this slow interpreted code to generate an audio frequency tone accurately by calculating timestamps. So period is, so clock frequency, I don't know how easily you can see the colors, but this, I should actually make this a little bigger probably. The special function registers are a slightly different color. So this is actually reading a special function register in the processor that calculates the current clock frequency given... There's a register that tells the... how does that actually work? I think that actually is not reading a register, but I think that's actually a built-in in spin. Because if you're... This is actually taxing my memory about what the propeller is doing. I forget whether that's calculated in hardware or in the compiler. Let's look that up. I think it's calculated in the compiler, but I think... All right, so this is the constant where we tell it what frequency the crystal is at. Oh no, that's actually Xin frequency. This is supposed to be the actual operating frequency. So, like up here, yeah, so we're not defining the clock frequency, but we are defining the crystal frequency and the clock mode, and then the tool is figuring out the clock frequency, which in this case is 80 megahertz, so 5 megahertz times 16. Yeah, I think the clock frequency built in that we were seeing is a compile time thing. I don't know, that's the current clock frequency. Oh, yes, okay. That makes sense. This totally looks like something that I would forget. So it isn't just hardware or the compiler, it's kind of both. There's a reserved location in RAM where traditionally you keep the actual clock frequency there, and so that's what this is reading. But when you change the clock frequency, it's tradition that you would also update that, which the spin interpreter does for you. That's partly why it's easier to set up the clock in spin, because if you set it up in assembly language, you have to know to update that. Yeah. Cool. So this is retrieving the current clock frequency from that value in RAM that's been calculated earlier. And then we're doing division on it. This processor does not have hardware multiply or divide. So this is actually kind of slow. But it doesn't really matter because none of this is time critical. And so we're calculating how many clock cycles per audio cycle here. Oh, and this is how long. So it's how many cycles to get to a certain length in milliseconds. And then we're initializing this. So timer, this is a local variable. This is how spin does local variables. These are declared on the stack. So you can do recursion. It'll eat up stack space if you put tons of stuff on there, but it's convenient. Yeah, and then, I mean, this idiom is really common. The thing where, so this is not necessarily the most readable if you're not used to assignment expressions or assignments being expressions, but spin kind of takes a cue from C-like languages where when you do a variable assignment, that assignment itself is also a value that you can use in expressions. And so in this case, it will update the timer by adding period to it, so kind of stepping it forward into the future, and then take that updated value and pass it to wait count. So it'll kind of sleep this particular processor core until it reaches that particular timestamp value, and then wake up with cycle accuracy. And then we're just emitting a pulse that's timed based on just how long it takes the interpreter to run this code, so it's not very accurate. So we just kind of repeat this command to waste time. Like the first one actually turns on the PWM, but these two are just to waste time, and this is turning it off. So that's fun. So beeping is done entirely on whatever thread of execution reaches this function. It doesn't interact with the actual motor driver. But then we have other cogs going on. What other cogs do we have? We have a sensor cog and a motion cog. So this is where we actually set them up. And we do the beep on the main initialization thread, like kind of overlapping with these cogs starting up, which is kind of weird, but I guess works. So we already looked at the pedal. So, for example, these are starting to get into more like higher level motion control things. So this is what it uses to try to move the needle up or down, run to position. In this case, position indicates like an angular position of like where it thinks the shaft of the machine is. And this is a lower level command, so you can see the motor open loop speed just sets some state in shared memory. So everything in spin is in shared memory, because when you're running the interpreted code, the interpreter itself is resident in that 2 kilobytes of per processor RAM. So that's not even, it's not even like local variables. Like local variables are on the stack, which is in shared memory. So like everything you do in spin goes out to shared memory, but like stuff that's built into the interpreter is fetched out of that local RAM. So that's where the code for the interpreter lives. Like, what even else is there? We could actually read the code for the interpreter, because I'm kind of curious. It's actually really dense, so I don't even know how much room they have for data. It might just be all code. Kind of curious about that. So this is the bootloader, but there's a separate record for the interpreter. Oh, and the runner. What is the runner? Oh, this is like a loader for the interpreter. That's cool. So this is stuff that they kind of wanted to load and then overwrite with useful interpreter code after things get going. That's useful. Yeah, they're probably not going to have a lot of extra space. I mean, this doesn't need to be big, but I mean, I think the interpreter is going to be packed. 2004. That was before I moved to California. Oh, that's cool. This is a nice ASCII art description of the bytecode language that it's interpreting. Ah, so nice. Very simple. Main loop, opcode. So this read byte is like the slowest thing we're doing, that like waits for the shared memory and reads a byte. It takes the same amount of time to read a byte as it takes to read a word from shared memory. So if you can read words, but sometimes you don't need that. All right, so then here's a jump table. So yeah, so jumping to the handler. So this colon jump is an instruction that gets overwritten. So move S right here takes T1, which is one of our temporaries. Because there aren't any actual processor registers, like there's just one flat chunk of RAM. There's just that 2K of RAM. There are no registers that are like more registery or less registery than that. It's just like all memory is the same amount of distance away from the processor, except for shared memory. But like, so you'll often see folks, so T1 is not actually anything special. It's just a memory location that we labeled. So there's probably going to be a list of those down here somewhere. Variables. So yeah, these are going to get reused for a bunch of things. That's one thing that's a little annoying when you're doing assembly language programming, is you do have to be really micromanagey about how you allocate memory a lot of the time, since you can't necessarily just like have the compiler figure out like which usages overlap. Like there is no compiler, so you have to, keep track of like, oh, I'm using temporary variable 1 here, and I'm using temporary variable 3 and 4 in this subroutine, and if I want to run them at the same time, that's fine, but now if I'm going to use this temporary over here, you kind of have to use comments to document that and be methodical. I mean, for things that share the same core, so things that run on different cogs have different memory, so it doesn't matter. Yeah, so we have constants, which also take up the same memory as everything else. But yeah, just a couple of these. These look like just temporary addresses for decoding the instructions, and then these are used for a bunch of things. But it doesn't. It probably doesn't have a lot of room for RAM storage in the cog. I mean, we could compile this and see how big it is, but this is probably most of the memory. So there's a bunch going on here. So there's a jump table that lets you kind of direct the flow of execution directly to one of these handlers. Anyway. So we have a bunch of these functions that just set up a motion mode and a target speed. Okay, and so there is a separate cog for PWM. So there's a sensor cog and a motion cog that are always running, but then the PWM cog starts and stops. I think I wanted to be able to do this to instantly stop the motor without having to like rely on the PWM cog to do anything. Oh, the motion cog is written in spin. So most of my separate processing cogs are assembly in this project, but that was an example of one that is actually written in spin. So like, yeah, so these are actually two different forms of cog new. Up here, motion cog is a spin function. So the spin compiler knows that, oh, this is the function variant of cog new. We need to set up an interpreter. In this case, this is just like a memory address. This is in the data section, so it's where the assembly code goes. And at just takes the address of it. If there wasn't an at there, it would just treat this as a variable, and it would read like the first word of the assembly code and pass that as a parameter. But instead, we pass like the address of the first word of the assembly as a parameter. And then this takes the address. So these are running kind of two different flows. This one is copying the sensor cog into the local RAM and then starting it running. And they're just passing this as a parameter. So this gets preloaded into that parameter register. And in this case, I think that's just the address of a shared, yeah, sensor cog data. This is an example of that thing I was talking about earlier where there aren't really high-level data structures in this language and you have to make do by using constants a lot. So in this case, it's just an array of integers, and we have constants for like what each of those array indexes are for, and we can use the same constants on the spin side and the assembly side. That's definitely one area where I kind of wish there was more integration between the assembly and the spin, like if you could define data structures that were visible on both sides of that boundary. So in this case, we have a pulse count, a position estimate, and then latched position when interrupt goes high or low. I forget if that's like a calibration setting or if it's something that's calculated dynamically. So the motion cog, when it gets run, it also has a parameter, but that's actually the stack because it needs stack space for in the spin interpreter. There's a default stack for the main thread of execution, because there's like a main thread. There's like a single entry point that runs on one processor. When you first boot up the system, you don't have any other processors. They're all sleeping, but you can choose to start them. But if you choose to start other processors that are also running the spin interpreter, they need a separate stack because they can't sort of fight over the same region of that shared memory, because the stack, again, is in shared memory. So the default like main thread of execution, I think it just starts the stack at the top of RAM and walks down, so you kind of get whatever RAM is left over. But if you want to have additional threads, you need to kind of carefully figure out how much stack space to give them. So that's another thing that's a little bit tough. There's some hints for that in the manual. Like you can try to calculate it, you can try to measure it, but yeah, you have to statically allocate the stack. So in this case, I have a 32 long stack for that motion cog routine. And that's where those local variables actually go. So like all this stuff here actually lives in that little stack I allocated. So this runs at a fixed rate. using that same idiom where you wait count on a counter that has its period already added to it. So in this case, motion loop hertz. And this is nice because you're really just guaranteed that this loop runs at that frequency. It'll wait until exactly the clock cycle you want. The pitfall is that if you overshoot, if you take too much time in this loop and you're trying to wait for a count that's already passed, the processor will just hang. So that's a danger with this. And if you want to avoid that, you've got to have some kind of like external watchdog on a different core that restarts that core if it needs to. Oh gosh, I'm doing like a whole filter thing here. So yeah, the reason this runs on spin is that I wanted to not have to write my own multiplier over and over again. So this is doing fixed point math. This is not floating point, but it's doing 32-bit by 32-bit 64-bit multiplication. So this double star operator takes two 32-bit numbers, multiplies them, and then gives you the upper 32 bits. So it's a great way to do fixed point scaling. So if you imagine that that whole 32-bit range of like 0 to all Fs, if you map that to 0 to 1, I mean it's not quite that. It's like if you had an extra bit, if you had 1 and then 32 zeros, then that would be 1. But this method gives you a really quick and easy way to multiply by any, approximate kind of real number between 0 and almost 1 in like one operator. And it's pretty efficient. There's actually a fairly nice way of writing multiply loops in assembly for this processor, but it does involve like looping in software to do multiplies. Again, something to keep the processor simple. I think the Propeller 2 is going to have a bunch of bells and whistles, like not just multiply and divide, but like built-in Cortex solvers and stuff like that. So yeah, Propeller 2 probably won't be quite so simple, but it's nice that Propeller 1 is still out there as kind of like a really minimal kind of reference model for some of these weird techniques that a lot of us like. So there's a separate cog that's just reading those pulses that come out of the speed sensor. I think it just stores the intervals between pulses in this variable, something like that. So it's a very noisy value, and then this filters it. And this is the actual servo loop. Oh, that's right. The open loop actually has an acceleration limiter. I forgot I added that. Interesting. So this just kind of ramps the speed linearly up or down to a particular target speed rather than changing it instantly. Okay, now we have some assembly cogs. This is where we would see any use of the brake if it exists. So we're initializing the direction here. So also each cog has its own direction register. So any cog can just at any time decide, oh, I want to make this pin an output and start writing to it. And then another cog can, it could also try to write to that pin, in which case I think the values get ORed together. It could be using the pin as an input just independently, and you could use the pin as like communication between cogs. You can do weird stuff like that. But I mean, mostly it is implemented that way just to make it easy to set up the I/O like on the processor that's actually doing the I/O. Like you don't have to configure it from elsewhere. It just kind of is pretty straightforward. And there are ways to do hardware PWM using the counters. I think the reason I didn't use that here is that I needed control over the duty cycle to limit the minimum pulse width, and I don't think I saw a good way of doing that with the hardware PWM unit. Oh, so I do have code here to set the direction pin. That's interesting. I was saying earlier I wasn't sure if I actually wanted to spend the cycles on like a bidirectional PWM, but that's exactly what I have here. So it lets you have a positive or a negative PWM input value here. So this read long just grabs one word out of shared memory, and this par is that second parameter to cognu. So this was just started with the address of the PWM input value, I think. Oh yeah, this gets past the address of the motor speed variable. So motor speed just turns into the result of that read long from the parameter address. Motor speed is right there. Current motor speed from minus FF to positive FF. Really, really getting our mileage out of that long there. I mean, it's convenient to use 32-bit for a lot of stuff, but like, if you're concerned about running low on RAM, then you can certainly use bytes in most places. Anyway, this like completely doesn't care about break. Like this is driving it low, but it doesn't actually do anything with it. This is also trying to be careful to set the direction at like not the same time as at the output, I think. That's interesting. I think I was trying to meet some timing constraints that LMD 18200 motor driver had. But this isn't as complicated as I thought I remembered it. Like, I don't think this is explicitly having to control for like minimum pulse length. I think it just gets that for free by how fast it's running. Anyway. Ooh, so then this is another cog running concurrently, simultaneously, which is just sampling the sensors. So is this, yeah, so it just loops this whole thing. So oh, interesting. So I think we're using a shift register here as a buffer of the last 32 samples. Is that what we're doing? This test instruction does a bitwise AND between these two values. So in A is the special function register with the GPIO inputs. Interrupt pin mask is this constant down here, which is shifted pin interrupter. So this just reads into the carry flag. We have to specifically tell it to write into the carry flag, since all the writes are optional and off by default in this instruction set. So we're transferring this bit into the carry flag and then shifting it into the shift register by 1, and then doing the same thing with the tachometer. And then, oh, what are we doing here? Tac shift, positive edge. Oh, we're comparing, so we're just testing to see whether the entire shift register is equal to this value. So we're looking for one low bit and then a bunch of ones. So it's just trying to do like a filter to get a very consistent edge. Like, it doesn't want to match like noisy bouncing inputs. It just wants to match, like, it was 0 for 1 or more clock cycles, and then it was 1 for at least 31 clock cycles. And so if that matches, this instruction adds tachometer count. Tac ratio. Oh, what is that? Something is adding to the current angle every time the tachometer. Yeah, okay, so this is our estimate of what proportion, like, this is just like how many pulses per revolution, really. So this is like a 360 degrees, basically. I mean, I guess that's this cycle then. So yeah, 16-bit shaft angles. they fit into a 32-bit value, so you can represent like a 1.0 like this, but it's really like 16.16 fixed point. So these, I think, are the needle up and needle down positions, which I think were just kind of experimentally, that seems about right. So yeah, that's just updating just a count of how many times the entire... Actually, why are we keeping both of those? That's interesting. I forget whether there's a good reason that we have both like an integer count and the angle, but like I think this position is much more useful, but maybe there was some reason I included that too for like debugging. Yeah, and then when we hit this position reference using the photo interrupter, so again, we're using one of these comparison masks. So just like it was high for 1 clock cycle and then low for 31 clock cycles. Oh wait, which side are we shifting this in? I think that's right. So shift RCL is rotate carry left. So new bits are shifting in on the right side and shifting towards the left. So the carry flag, if you can imagine, is sort of in between the left and right side of this, and it circles around. So we're shifting left, the carry flag flows into the least significant bit here, and then you have a buffer of 32 bits before the oldest bit then kind of falls off the top. So in this case, the oldest bit is 0, and then the 31 newer bits are all 1, and then vice versa. Yeah, so I think the way I did this was I just like splat a particular calibrated position onto the current angle reference when the photo interrupter hits a state. So this is, and I think I just adjusted these constants until it seemed about right. But these just represent the angle at which the photo interrupter enters the low state or the high state. And it doesn't try to filter this or anything. Like you can imagine maybe like having something self-calibrating that, like, I don't know, I mean, you still need like some kind of absolute position reference, like, so, but you could calibrate at least one of these automatically. I think I just, found some values that seemed to work. So then after all that, this is just kind of taking some time to write stuff back to shared memory. So T1 is a temp that I'm putting the address of this whole structure in, and then just like writing things back in sequence, adding 4, writing the next thing. And this ends up, like this add is pretty much free because you can't just call write one after another without like waiting, I think, at least 3 cycles for the next hub window. So I think this add just like fits in there and you get it pretty much free. I don't know. It's pretty simple. So yeah, we could completely just remove the break pin if we needed to. We're only using PWM. And there's code for direction, but it's not even important right now. So that was a nice detour. Let's see where the noise is coming from. Oh, I need to fix the chat, sorry. Interesting question from Crazy Hair Guy who wants to know if it's not possible to do weird multiplication with bit shifts and addition or subtraction. Oh yeah, I mean, I think, are you talking about like optimized multiplies and divides where, so like you can think of any multiply as repeated addition, right? And you can think of binary multiplication as sort of one addition per 1 bit in one of the numbers you're multiplying. So you could figure out like which of your 2 numbers you're multiplying has the fewest bits that are set to 1. And then for each of those 1 bits, you take the other number you're multiplying and shift it by that amount. and then add all those together. Like that's just like a basic kind of optimized multiply. And if you have information about what those numbers are at compile time, you can just kind of bake that code at compile time to do the optimal flavor of multiplication rather than having to rely on your CPU to do that. So yeah, you can certainly write custom multipliers if you know that your values are going to be in a certain range. The spin compiler won't do that for you. But if you're writing assembly, you've got to write your own multipliers anyway, so you can write special purpose multipliers. I've certainly done that. What project was that for? I think that was for the weird Ethernet driver. Yeah, the weirdest code I've written for this processor, even weirder than the USB host controller, was this very strange Ethernet driver and networking stack. But that is definitely like a whole rabbit hole. That was super complicated, and one of those projects where I have no idea why I spent so much time on it. I think the goal I was trying to work toward is I wanted a propeller-based network music player. So I wanted to be able to send audio from like an open source application of kind of arbitrary description over Ethernet to a wired speaker that would play it in real time. Pretty standard kind of stuff that you could just do with a Raspberry Pi today. But I wanted to try doing something that was kind of more like microcontroller-y and using really small amounts of RAM and really low latency and just trying to kind of keep things pretty close to real time. So I ended up writing my own SPDIF, like optical digital audio modulator for the propeller. So I ran that on one core. I think that took one core, maybe more. I think it just needs one core. It's pretty simple, but it does involve like this thing, I think it's called biphase mark coding or something. It's like related to Manchester encoding. It's like each bit turns into 2 bits with a phase polarity that depends on whether the original bit was a 1 or a 0. There's stuff like that, like you have to format these packets correctly and then it's audio. So I have one module for the propeller where you just give it like a buffer with audio samples and it modulates the SPDIF out of a general purpose IO pin. You can literally just connect an LED to the propeller and play audio this way. I made some demos that play music off of SD cards and play like synthesized audio. So I had that, and then I made this whole huge complicated Ethernet contraption. It was all based on this hardware Ethernet controller from Microchip called the ENC28J60, I think, which was one of those chips at the time that I kind of hoped it would die and be replaced by something better because it was just so buggy. Like, it has so much errata, but that chip survived a lot longer than I expect. Like, I don't know if there's actually a better option for it now. I mean, not a lot of people are as into retrofitting microcontrollers that don't come with Ethernet, and not as many people are interested in 10BASE-T, but like that's still a chip that I think people use. Like, I think you can still like connect it to your Raspberry Pi and like add a second Ethernet port that way. But it's a 10BASE-T controller that you talk to over SPI. So it has the MAC and PHY layers, and it has some RAM. So you still have to implement the network stack in software. I think you still have to do checksumming in software because even though they tried to implement it in hardware, it's like too buggy to use. There's a bunch of errata about like IP checksumming and TCP checksumming. But yeah, it gives you some RAM. You write packets into the RAM and then tell it to send the packets. And it has like a receiver and a MAC address filter. It's like a really basic network adapter. So I wrote propeller code on top of that in many layers, like starting with one of these. I think I used that really ridiculously optimized 10 megahertz SPI bitbang core for that. And then I also, I had like an assembly language core that was sort of like a network offload stack. So you have this shared memory buffer where you assemble like chains of socket buffers. So you could have like buffers in shared memory and then say like, oh, I want to wrap this buffer in like a TCP packet and then send it out and like have a data structure that just represents that operation. And so you could have like a main thread of execution that made like socket API calls that filled out these data structures. And then this other network offload processor would run through these data structures and generate packets and send buffers over to the SPI processor. And it was very complicated. And then so on top of that, I had like a UDP-based audio transport. So I did implement TCP for this thing, but I wanted to use UDP for the audio anyway. I ended up Yeah, that was pretty weird. I didn't want to have to buffer a bunch of audio, and I wanted it to be basically like a broadcast device rather than a bidirectional thing. So I wanted to just be able to send out packets at the correct rate from the transmitter and then have the receiver adapt to that rate. So it actually had a phase locked loop that would try to synchronize a local clock with the rate that the audio was actually coming in at over UDP, and then use that clock to generate the SPDIF audio clock, which was then generated, or that was then used as a reference for your actual audio DAC. So, uh, it kind of worked. I had trouble with the frequency stability, as you might imagine, but I got it kind of able to play audio. It was uncompressed. It was not sending MP3 or anything. It was sending like uncompressed PCM audio over UDP, but it was still kind of fun. I don't know if there's room for this. Maybe I can. I think I need a minor restroom and hydration break anyway. I'll be right back. Oh, this has been such a rambly stream. It's already like 3 o'clock and we haven't even opened the motor controller box. Let me know if you think this is too rambly or not rambly enough, or just whatever.
I like the Rambly. It's kind of like the Siftio stream you did a long time ago.
Oh, that's good. Glad, glad it's good. 2 volts per division. DC coupling. Let's not have the coax for the oscope probe in the sewing machine. Okay. Well, so I think the only pin that's even connected at this point is, PWM break. So I'm just going to first check break to see if I can rule out that being a source of noise or whatever. I think it is probably going to be more interesting to look at PWM, but let's just try them both. So... I guess the hook is really the best tool for this. I was just going to do a quick probe, but, maybe not. What is that? I don't know what that's coming from. Is that just a bad ground? Yes. Thanks, bad ground. Making yourself known early. Okay, that was the brake pulsing a bit during initialization. Oh, did I actually grab PWM and not brake? Oh, I did. Okay, well, I guess we're looking at this first. So this is the side of the resistor closest to the motor driver, not the microcontroller. You can definitely see the servo loop oscillating a bit. Let's try open loop mode just to have something a little easier to pin down. I might load that other program that's simpler and just runs open loop mode. Let's try getting this going at the minimum speed. I think the minimum pulse length is supposed to be like 1 microsecond, so that seems fine. Check out that ringing. There's the crash. Okay, well, let's check the other pin. I'm just going to check like all the combinations here. I want to look at the brake and the PWM on both sides of that resistor. Yeah, right. This is a significantly overkill sewing or a O-scope for a sewing machine, but it is nice to have it. Okay, this should be brake on the motor controller side. Ooh. Not the first time turning on the sewing machine has disrupted one of my video connections. Really? Is this another ground problem? Yeah. Okay, brake looks pretty clean. I don't see any problem there. I'm still not really sure whether the problem is on the I/O or the power side, or maybe some combination. And there's the microcontroller pin for PWM. That looks pretty clean. Oh, let's servo mode again. Could probably stand to clean this thing. That's open loop. Good amount of that ringing does make it through. I mean, the amplitude isn't very high, but it still seems like that's more than you want. know if this would be enough to crash it, though. I mean, that bounce below ground is not happy. You know, it's possible I've got a better ground at this point, and it might give me more information to look at the 3v3 rail with this nicer ground. Precarious. Let's see how noisy this gets. Wait, that was... what was that? Oh, these grounds are terrible. I should just solder on a new ground. I wonder how much of the problem is just like corrosion on the ground pins on the I/O connectors or something like that. Is that it? That seems better. Ah, it's already crashed. You know, I wonder if this actually isn't even related to the motor controller, but it's related to that bad choice of resistor on the input to the tachometer sensor. That doesn't look great. I mean, it doesn't look terrible, but Thanks for resetting my video scaler.
Oh, it's the EMI from the sewing machine actually killing the video scaler?
Mm-hmm. Yeah, it's done that to multiple monitors here. The O-scope and my two monitors here have both flickered before when I've turned the sewing machine on. I don't know if it's the motor or if it was the inrush current from the just like turning the power on. I mean, I'm not convinced I know what the specific problem is. There's also part of me that thinks I should just open the motor controllers and start throwing capacitors in there. But it'd be nice to have more of a smoking gun here. I'm wondering how much variation there is even just between the different grounds in this circuit, because I think that might have been tripping me up earlier. So I wonder if I could use this nice solid ground over here and then probe the negative end of this capacitor over here by the processor. Whoa. That is kind of noisier than I expected it to be. What Where did that come from? Corrosion on the ground. Yeah, okay. But yeah, that's interesting. This is on 500 millivolts. This is between two grounds. E. I wonder if that's coming through that negative edge ringing on the PWM pin. I don't know what's actually like coming through the IOs and what just happens to be synchronized with the IOs, because like that's what's triggering the motor. Tempted to just like temporarily add a capacitor to see how it changes that waveform. More bypass is always the option. I mean, I'm pretty sure that's the solution. It would just be nice to have a more complete picture of what's going on, but yeah, that's probably where this is headed. Capacitor bin. Are any of these good? I've got some 1 nanofarad, which might be alright for the IOs. I might just put these across the IO pins in the motor driver, like just in that box. 1 microfarad ceramic at 10 volts DC. That does not help. Ooh, aluminum 560 microfarads, 25 volts might do. No idea what the ESR is like though. Tantalum at 6.3 volts. Kerpow. That's not what we want. What was I doing with 10 volt rated 1 microfarad ceramic? I think you have to wonder what the actual capacitance is at a particular DC bias voltage with those. What are these? This is just EMI coming from somewhere. The sewing machine's off, but it's confusing me. The heck? I mean, this looks like power supply noise. Is this power supply super noisy? That would be funny. You know, when I first built this sewing machine, I don't think I had a bench supply that was powerful enough to run this, but I think I do now. Forget what the rating is on this. I think this one goes up to 5 amps. Gosh. So, is that all noise in the ground? Because, I mean, this is me measuring between two different grounds on the circuit. So this difference that I'm measuring, I mean, either there's like a ground loop between the O-scope and this power supply, or like that really does represent some like high frequency like current flow on the ground. Like, how is this happening? Oh, is that all RF? Okay, what if I just clip this to the ground on here? No? Oh. I'm just holding the probe near the motor controller box. So, does it change if I ground this? Oh. No, that's coming out of the positive side. Okay, I just touched the outside, the insulated side of the banana jack on the power supply. I think that might just be conducting through a combination of the air and my body. This power supply is nuts. How much? I mean, this is a high impedance probe, right? But that is registering like, what, 8 volts peak to peak? 10 volts? I wonder if the capacitors in this power supply are dried out. That would be an interesting root cause for all this. Ugh. I'm just going to find some long enough banana cables I can plug this into a different power supply for the moment. These banana cables are also kind of corroded. Wow. It's acoustically and electrically noisy. Oh, the noise appeared right when I came back. Yeah, it might have been coupling through my body might have been amplifying the coupling between the power supply and the O-scope probe. I need a better place to store these wires. I always wanted to have just like a hanging wire holder thing for these banana plugs. I just always have to keep them away from my cat. But there's a closet in here now, so I think I might make one of those on the inside door, or inside of the closet door. So I can keep it closed. Keep all my wires handy, but away from the cat's mouth. I also don't have long enough banana cables, so I'm probably gonna have to stick 2 of them together. This always makes me nervous because I don't know how low resistance these really are. Should get a proper setup for testing that. You know, just like run some current through them and I think I did that actually. I think I did just like do at least that. Excuse me. Stay safe out there. Yeah. Sorry. Microphone cable keeps getting stuck. I think I'm missing some like shirt clip or something I'm supposed to have to keep the microphone cable from getting stuck. It's probably with my microphone stuff somewhere that I've neglected. It'd be funny if like most of the problem was the power supply. I mean, don't get me wrong, there are plenty of mistakes in this circuit, but it's interesting that it seems unclear that the specific mistakes are causing the specific symptoms at this point. I mean, it's definitely worth throwing some more capacitors in that motor controller though, because it needs some low ESR, like ceramic preferably, capacitors in there. Some tape to keep these from touching each other. Okay. Banana time. Set it to 12 volts and crank up the current limit. Not bad. 200 milliamps at 12 volts. Well, 180 milliamps. It definitely still crashes on this power supply. Alright, well, seems like we have multiple problems, which is not surprising. 440 milliamps now. Yeah, it doesn't even need an especially beefy power supply most of the time. I mean, it'll definitely use more current when you're cutting, or when you're sewing like thick fabrics. This power supply is also quieter, which is nice. It's really nice to have a place for projects where I can keep Tuco out of here if I need to. Like right now, he's somewhere else, presumably behaving himself. But like, I wouldn't have been able to leave any of this wiring out at all for any length of time at the old place. Some capacitors to stack. Yeah, we could certainly try that. Yeah, I mean, it might just be time to try opening up the motor controller and adding the capacitors that seem like they should obviously be there, and then debugging further. At the very least, it might even be easier to probe around in the motor controller box, because all the noisy pins are going to be right next to each other. Alright, let's turn that off for now. I did have diagrams with like the color codes for these ribbon cables at least, which might be handy. I think these are also pretty straightforward in that they just mostly just go to a pin on the LMD18200 chip. Ah, flat-bladed. Really? What kind of monster designed this? Sorry. Ah. Gosh. I have a couple of power supplies now that are like super noisy and have warnings on them to that effect. I mean, this one I think is intended for like automotive stuff mostly, so I feel like it's hard to tell whether there's something that's failing in here or whether they just always assumed that whatever you're plugging into it has plenty of its own filtering. I hate this thing already. So this wire was, I guess, my attempt to do additional grounding of the motor frame for radiated EMI. Shouldn't have been my top concern, really. Looks like these are the pins that I am no longer using. Oh, did I actually disconnect everything except for just the PWM? Let's get a schematic. Okay, that's actually in the same orientation. Okay, so the pins on the top and bottom are, they're labeled boot for bootstrap. They call that in the datasheet a bootstrap capacitor. It's sort of like a charge pump for turning on the MOSFET drivers. Actually, is this even a MOSFET? I thought this was not a MOSFET-based circuit. I thought this used Darlingtons for some reason. Let's look at the datasheet. Oh, hey, Tuco. What's Tuco looking at? Tuco, is there anything interesting out there? There is a pile of recycling. And now Tuco's sitting on my laptop and filling up the password prompt. Good job, Tuco. Very cat. Tuco, what are you doing? Oh, he's gonna break those blinds too. Tuco, you really love causing metal fatigue. Boy, boy. Hey. Mm-hmm. Hey. Hey. That boy. $18,200D. What is the D for? Is that DMOS? Maybe the D is just the package. Hey, oh gosh, Tuco, what was that about? Gosh, boy, boy. Oh, I wonder if it's time for me to shut Tuco out for a while. This is increasing stress levels. I guess it's built-in MOSFETs. DMOS power devices. Yeah, charge pump, H-bridge, good stuff. Built-in flyback diodes too. So bootstrap, output. Is that going to a really thin wire or what? What is going on in here? Oh, is it focusing on the top edge of this box? What is going on with the white and gray wire there? That just doesn't look right. So oh, there's the motor wires. They're hiding underneath. Okay. So this red and this black that's underneath the black heat shrink are the motor wires, which look correct. They're attached to the bypass capacitors and to the second pin on each end. These other red and black wires are the power input. So this junction here is ground. I think what I did here is that these were originally some of the inputs that I decided to unhook to see if I could mitigate potential like noise issues by like just grounding unused inputs. So I think I just cut those wires and then soldered them to this ground point, which is why that's kind of weird. So pin 1, bootstrap, pin 2, motor. Pin 3 goes to the white wire, which is grounded. So that's the direction input. So direction is just grounded here in the motor driver. And this is the other end of the white wire, which has been cut off and heat shrink covered. So yeah, no direction, as usual. Then the next is the brake input, which is the gray wire, which is also grounded. Then we have the PWM input, which is this purple wire, which is still connected. I think that's the only one that's still connected. Then we have the minus power supply. Or no, that's positive, yeah. Which looks alright. That's soldered pretty much directly to that beefy red wire. There should be a capacitor there, but there isn't. Instead, the electrolytic capacitor is just wired across the switch. Okay. It's like way over there. Oh no, sorry, I misread this. So the wire... okay, so this is just a junction between the actual motor wires and these thinner wires that are soldered to the LMD18200D. But then here's power coming in. Goes to the on-off switch, which has a light in it. Then this is the other pole of the switch. So we've got a thin wire going directly to the DC converter board. And then this thick wire going over to the electrolytic capacitor, and then also coming back to this zip tie point. That's not terrible. It's just, these wires are so long, and mechanically they needed to be because of the size of all this stuff, but it's not good. I just need to find, just like squeeze in some more capacitors. So I think I'll want to take off this PWM lead and solder on like a surface mount ceramic capacitor there. Maybe find a better way to like mechanically anchor this. And find some place to put capacitors. Where's the ground? I think just between these two pins. Pins 6 and 7 on the LMD18200 just should have a bunch of low ESR capacitance. This is annoying. Oh man, I'm liking this new video recording setup. I've got simultaneous synchronized recordings from all the devices so that I have less terrible organization to do later before I can edit. There's just very little room. I attached this piece of wood to the front, which was useful when I had this mounted in a cart, but now it's just completely in the way. It doesn't even really show up on camera. I don't know that I care to move the camera right now. Just add capacitors. Yeah, maybe. Somewhere I've got a stash of really nice high-value low ESR ceramic capacitors that I was using for power supply filtering in a different project. So I might have to rummage around and find those and then put them in on a future stream. I've actually, I don't know, I think I got over the initial, like, social anxiety of starting the stream, and this feels okay, but I do actually have to leave before 5. I'm trying to actually do some, like, getting involved with local organizing, and I've got to have, like, a phone call with someone. But I'm just so bad at all of these things. Uh, Take the screws off the sewing machine so I can move the sewing machine back on the table so I can fit the microscope in front of the sewing machine so I can solder under the microscope. Calendar alerts. Yeah. I keep meaning to switch my calendar over to Nextcloud because I've been using it for so many other things. I have, for a lot of these things, I'll end up setting like alarms on my phone instead of the calendar because I can't ignore the alarm as easily. In fact, I think I'm going to have an alarm going off in like 15 minutes to remind myself to get ready for this other thing. Oh, right, the bottom of this is not actually flat. It used to have feet, but the feet fell off at some point. Got a piece of wood now. Yeah, this had big chunky rubber feet, which I think mostly broke off. And then I, for a while, had this mounted in like a rolling sewing cart. And that piece of wood was useful because it kind of kept it centered in the cart. I need to find a better way to have a desk in here. Gosh, I feel like this is going to tear up my table unless I put something under it. This camera is still quite warm to the touch, but hasn't complained at me for overheating yet. I'm only recording in 1080p right now, though, which probably helps. Hey, Tuco, you're back for more. What do you want, Tuco? He just comes right in and sniffs at the pile of cables like, oh, is there anything in here I can bite? Oh yeah, you want to bite some Ethernet cable. I know this mood. Get away from there. Hey, hey. Hey, Tuco. No. Oh, he is just chomping right at this network cable. Honey boy. Do you want attention? No, honey, that's an audio cable, also not chomping. I'm gonna have to close the door. Hey, boy. Let's have some space. Oh, he wants the door open. I guess it's cooled off enough I could turn the air conditioner off and open the door for him. Meow. Tuco, do you want the outside? Oh, it is kind of toasty outside. Ooh, look at the warmness happening. What actually is the temperature? I don't have an outdoor thermometer, but I can ask the internet what the weather is. Oh, the internet says that it's 90 Fahrenheit, which is 32 Celsius. That's kind of toasty. Today it was supposed to be some kind of heat wave. Like, it'll be a little cooler tomorrow, 32 Celsius. Yeah, I guess the high today is supposed to be 91. Yeah, definitely warmer than it got at the old place. I was hanging out in the garage a little bit early this morning, and that was actually super nice, though. Tuco seems to like that spot. Has no concept of packets, but sniffs all the time. Yeah, that's good. Oh. That's kind of a fun view. That camera angle is super weird because the camera is not mounted in a at all permanent way. It's just kind of like hanging off the wall. I need to get that mounted better. Pretty much all the wiring stuff I've been putting off. Well, now because of the pandemic, but before the pandemic, I was trying to kind of make sure that I felt really confident about the locations that things were going in, and it was hard to achieve that without knowing what summer was like here. So far, the warmness seems all right. Like this room, as we've discovered, does need occasional air conditioning if I'm running a bunch of equipment. Um, the front of the house is just more spacious. Like this room is just a lot of equipment in a small area, whereas the actual machines running this are in a rack at in the other side of their house, and it's in just like the living room, so it has a lot more air circulation anyway. Oh, Tuco. Is that 54 degrees for you, Thomas? That is definitely a different temperature than we're getting here. Yeah, gosh, the warmness certainly just like pours in with the door open. Tuco seems to like it. Hmm. I need a place to put little loose screws and stuff. Gosh, weather like this kind of makes me want a cold drink. Got some orange juice. Hmm. Oh, I guess I got some water and then forgot to bring it back in here. So there's that. It's annoying not having connectors or anything. Speaking of warmness, maybe I'll turn off the oscilloscope. That oscilloscope is actually pretty power hungry. It's like several hundred watts all by itself. Actually, I've got a graph for this. also can't believe that happened earlier. What has the network been like since? Oh, that's much better. Just not even 100 megabits of internet, which is more usual. Oh, hey, Tuco, what are you doing over here? Hey. Okay, like 130 watts, I guess, for a pretty much idling oscilloscope with one channel enabled. Hey, Tuco. All right. Capacitors then. Yeah, I mean, I'm inclined to try these 1 nanofarad capacitors for the data lines. I mean, for power, I guess I could start with like maybe both a 0.1 microfarad and one of these couple hundred microfarad electrolytics. Big stack of surface mount capacitors would certainly do the trick, though. I mean, if anything does. Okay, well maybe I'll start with the data pin capacitor, and then we might have to save the rest of this for a subsequent stream. Gosh, how does the ground even work here? You know, that's probably part of the problem is that the like the ground that the microcontroller is referenced to is coming from. Oh, I don't even have the right camera up. Sorry. The ground that the microcontroller is getting comes from all the way over here on this DC-DC converter board. So it might just be like there isn't nearly enough of a solid connection between those grounds. So like that point on the circuit board is sort of trying to be my high power star ground, but the microcontroller gets its power through this ribbon cable, tiny ribbon cable, which comes from this side of this board. I don't even know how solid of a connection there is between the ground on the left side of the board and the right side of the board, because like I didn't design this board, it's just from a car charger. And that's how the ground reference for the logic is going through the car charger. Design problems. So yeah, I might unstick this board just to look at the back of it, or I might just like connect the grounds more. But then, so like best case, the ground is going through this circuit board without any intervening like resistance or inductance, and connected to this ground wire, which is also tiny and loops all the way around here, and then back up here, and then connects to the switch. Which is, yeah, that's not great, and it's definitely going to couple some of the motor noise into this ground. Yeah. Gosh, it's hard to tell how much it's worth just trying to like patch this thing up and how much I just want to redesign it. But I know that that urge to redesign things is usually not helpful, but it certainly might be in this case. Mild definition of 0 volts. Yeah, it's not a very solid ground, right? I mean that seems to be the what we're observing here is that the grounding in this whole circuit is just not great. Oh, this is going to be like kind of halfway deteriorated foam tape holding it on. This stuff is so gross when it deteriorates. Gosh, it's always fun to take apart embarrassing things that your past self designed. I have some maybe better DC converters we could use, but it's not clear that the converter itself has anything wrong with it. Like, I didn't notice undue noise on the 3v3. I guess I didn't check the 6-volt rail, because there's a linear regulator on the other board that goes from 6 volts down to 3.3. But the 3.3 looked pretty good. Probably worth checking the 6 volts, but it does seem like the problem is more about like ground than power supply noise. I mean, ground noise rather than noise that's coming from the power supply. This little piece of Kapton tape. That's funny. Warranty void? Yes. Oh no, I avoided the warranty. Okay, so it is just a straightforward ground connection through this winding PCB trace that goes next to, I don't know, not much. Oh, did I double up on these thin wires? Gosh, the wiring might be part of the problem too, because this is ribbon cable that I got from, oh, I think the same surplus store that I got the motor from. And it's not very thick, and it's also got insulation that's already turning gummy and gross. So replacing some of the wiring might be another thing that could improve this situation. Like, this whole wiring harness doesn't need to be this complicated. All it is 6 volts and a PWM signal at this point. Like, I don't think I care about preserving the direction control here. I mean, that might be interesting, but I mean, I'm more interested in just getting this working back up to the same level of functionality I expected before, but without the crashes. I mean, I think I used this awful ribbon cable because I wanted, like, the insulation displacement style connectors on the other side, because that's what I had. It's just not very good wire. I mean, this isn't super high current, but even a couple hundred milliamps, it's, like, probably not the best thing for this wire. I don't know. I'm more worried about the noise than the resistance, but ugh. Like, I'm not super concerned about this red wire being kind of circuitous, but all this grounding could really go. Just noticing that this DC-DC converter also has, it's relying on these electrolytic capacitors to do all of the capacitance. It hasn't got any ceramic or tantalum capacitors. Those unpopulated footprints are for an indicator LED, which I think I desoldered actually. I think it did actually have that. There's a slot which I think was just for mounting. I mean, he's got this one tiny... Oh, that's the alarm I set. Phone and the water were right next to each other. Well, maybe this is a decent stopping point for today's stream. I feel like we did a bunch of rambling and had some unrelated technical trouble, and then kind of sussed out the general outline of the problem here. I mean, it seems to be mostly just the lack of proper decoupling and grounding in the motor controller. There are some other things it could be, but it seems like it's mostly that. So maybe we'll hang out for a little bit longer, and I might fuss with this a little bit, but kind of try to wrap it up, and then we'll start this again probably tomorrow with more of this, with maybe some better capacitors if I can find some. If not, we'll make do with this. Oh, a few amps. Oh, there's definitely not a few amps on these wires, but I think at most a couple hundred milliamps. But like these are a few amps, but I think they're fine for that. This is just powering the control circuitry. Trying to, at least. This purple zip tie is cute, but it also seems to be kind of in the way at this point. Let's also just trim that. Gosh, I just don't like any of these thin-ass wires. It's not my thing. What would it take to replace this whole cable? I mean, really anything that's on 0.1 inch headers. So, can probably come up with something. I might have to rummage around in the garage a bit. But that could be on the list of things to have for next stream. I don't have exhaustive header crimping stuff here. I have like a little bit of header crimping stuff, but probably not anything that's super useful for this. I've been doing a bad job at keeping an eye on the multiple chats on this stream, haven't I? Oh yeah, the propeller is definitely good at LCD driving. Yeah, I mean, it's a great processor for doing like kind of old school graphics stuff. It's not a great processor if you want to port any modern graphics libraries. Like, don't expect to use any existing software if you use the propeller. Just expect you're going to have to write everything from scratch. But if you like that sort of thing, it's a great platform. Oh, that's a good question. Signs of Rain from Twitch chat wonders how Kirby's blinks are timed. I don't know the answer to that off the top of my head, but we can definitely look at the code. Let's let this camera cool off. Kirby, how do you work? Okay, so I think, yeah, like, so I guess we were looking at the sewing machine file and like how the actual motion control works, but we completely skipped over the main program. Um, and so we've got like small substitute main programs that look kind of like this. This is like the minimum viable sewing machine controller. If I loaded this onto the propeller right now, well, if the propeller had power, which I just cut the power wires, but once we fix that, if I loaded this on, it would print some debug to the serial port, but mostly what it's doing is just reading the pedal and then setting the speed to the whatever the pedal reading is without even like scaling it or anything. But the actual main that I have loaded on there is a bit longer. Yeah, like 400 lines or something. So let's see, we have some additional pins. So I don't even think I have these on the schematic, but this is like the documentation of where the UI is connected. Oh yeah, it's got a 3-color LED. This was sort of a UI kind of board from SparkFun. So like in addition to the LCD itself, it has a RGB LED and a couple of buttons. So I just have pins for those too. Oh yeah, and there's an encoder wheel. I think this is part of the Parallax standard library, this quadrature encoder module. Or is that something in here? Yeah, I think that's a standard library module. And float math is also a standard library module. Same with simple numbers. But this Nokia 6100 is something I wrote that's in the same directory. And then what is, I think simple debounce is also mine. Oh yeah. Oh yeah. I was mad about this because there was a debouncer that was pretty popular, but it used like an entire CPU core to just do its debouncing, which seemed like something I didn't want. So this is just like a little shift register thing that you can call from spin code. Very straightforward. So yeah, these variables that start with cute, I think in the code I called Kirby the cuteness. Like that was the object that added cuteness to the program. So we're initializing all the stuff, initializing the LED or LCD, and then changing the color to green, and then main loop. So sample the buttons. This is the debouncer. Read wheel steps is, I assume, something to deal with the quadrature input. I think wheel raw is coming from the quadrature cog. Yeah. So the quadrature encoder writes something to wheel raw. I forget how that actually works. I could read the documentation for that quadrature module. Low pass filter for the RPM estimate. Yeah, we do some drawing on the LCD for some of these debug boxes and things. Let's go back to the main loop. So main loop, button sample, read wheel steps. These are just preparing inputs, and then we have some like UI portions of the main loop. Highlight. Oh yeah. So there's like a mode where, I don't know if you noticed how I was using the wheel because it was kind of off screen, but there's a mode where if you turn the control wheel, it's selecting a menu item, and then there's a mode where it's changing what that menu item is set to, and you toggle between those by clicking the control wheel. And it tells you which one you're in based on the LED color, I think. I think there's like a highlight that changes also, but I figured the LED would also be a nice indicator to add on. And so it's only running, it only actually runs this sewing control thread, or like procedure, when it's in that normal mode and you're not editing. And this just runs via polling, like it just repeatedly at some constant rate. Is it a constant rate? Maybe it's just as fast as it can. I think it just runs this loop as fast as it feels like. And every time through the loop, it updates based on one of these modes. Let's see. So handle buttons, draw menus, draw instruments. So we're just checking the debouncer for these. Yeah. So I tried to have a soft reboot, but that doesn't actually unhang the processor if the processor is wedged in certain ways. Yes, yes. Menu stuff. Button enter is the clicking the wheel. Alright, draw menus. So this is all drawing on a frame buffer. Or no, is it? That's right! This draws directly to the LCD's internal frame buffer. So it doesn't actually, at least I think that's how this works. I don't think we have a double buffer in the propeller's memory. I think it uses only memory on the LCD controller. Now I'm curious about that. Yeah, there's no frame buffer here. So like text, I think, is taking each character and scaling it out of ROM. Yeah, so this is very light on memory. And this is asynchronous, so yeah, the text string, it just references the text, sends a pointer to the text over to the rendering routine in this driver cog. So when you're drawing text, reads a character, calculates the address for the character cell, scales the font and blends it with the foreground and background color. Yeah, it pre-calculates a palette because it's got like a lookup table for going from like a black and white row of pixels at one resolution to like an interpolated row of pixels at the other resolution. And then it has a table of what actual colors those different interpolation values map to. And the table only needs to be calculated once per when you change the foreground and background colors. Yeah. I like graphics drivers that don't require that you use tons of RAM. Like if you want a RAM frame buffer, you can have one, but it works without one, which I like. But it means it's not double buffered. I don't think we have a double buffer in the LCD controller. I think we're just writing to the front buffer here. Otherwise there'd be like a page flip here. But I don't think we have enough memory to do hardware double buffering. So like when it's drawing this text, it's not drawing like an opaque color on top of a transparent background. It's converting a black and white image to a colored image using the lookup table and then drawing all the pixels. So if you don't move the text around, it'll just perfectly overdraw whatever was there without any flickering. Draw instruments. There we go. Text is boring. Also graphically represent the speed with a cute sprite. Here's the sleepy animation. Oh, it's using the spin random number generator. This is a built-in function in spin, if I remember right. Oh, that's right. There's a pseudo-random number generator operator in spin. It's another very weird quirk of this language. So rand is actually the state variable for the random number generator. I'm wondering if we use that state anywhere else or if it's only used for that. Yeah, it's only that. So we don't initialize it, so it gets initialized to 0 like the rest of RAM. and then we're just iterating a pseudo-random sequence. So that generates just like a pseudo-random sequence of 32-bit numbers, and we're only using the bottom 4 bits of that. So it should have approximately a 1 in 16 chance every time this code runs of going into the sleepy state instead of the idle state. So how often does this run? Oh, that's right. So this whole loop only runs as frequently as this RPM period. So every RPM period often, which I think is like 100 hertz or something. Let's take a look. Oops. 5 hertz. Okay. That's not the rate that it like updates the motion at. That's the rate that it like draws the state at. So 5 times a second it updates the LCD, draws a new RPM and all that. And during that decision, 5 times a second, there's a 1 in 16 chance that Kirby blinks. So how does cuteness frame work? And then here's the walk animation. Oh. So that's just a wrapper around this LCD image routine with the coordinates it's drawn at, and then a sprite from this table, which is this binary file we import. I forget, I must have had a tool to generate this. I might have been able to save it directly from an image editor as a raw image, because I think this is just a raw 16-bit per pixel image. I'm just like hard-coded this as like a sprite strip. Yep, so that's how the Kirby blinks works. That's how the whole UI works pretty much. Yeah, just to update the Orb2 from the chat, who's wondering if it's still an EMI issue or not. Yeah, no, it does seem like EMI. I don't have like a precise smoking gun. Like I don't know whether it's like radiated or conducted or like specifically where it's going through, but I've got a pretty strong hunch based on what we've been seeing so far that it has to do with a difference in the ground that the motor controller is using versus the ground that the CPU is using. And I think there's some noise current like between those two not very well coupled grounds, which is then causing the PWM pin to go negative for a little while, which is then kind of probably causing some current to flow through the ESD diodes and or the microcontroller's ground in a bad way. So it seems to be something along the lines of like the PWM pin bouncing below ground or the ground reference itself being flawed. Like we saw some kind of concerning levels of ground noise just between 2 different ground references on the microcontroller board. So that's something else to look into. But I think the first thing to do is just clean up the really obvious sources of noise in the motor controller box. So I'm trying to wrap this stream up, but I think when I start up on this next time, I'm just going to try adding some of these obvious capacitors to the inputs and outputs of the motor controller, to the PWM pin, and do the grounding in a less terrible way. Maybe use thicker wire for especially the power and ground going to the microcontroller board and just see how that does. So much of this is almost the worst possible design, like having the motor controller and the power supply with their grounds kind of connected in this not great way where we're kind of sharing. So some of the current that's flowing between the ground and the power supply and the ground and the motor controller is also inducing like a voltage change in the microcontroller's ground relative to that motor controller ground, the way it's connected right now. And I'm pretty sure that's at least part of the problem. Oh, Tuco is having a great time. Let's see if we can get Tuco on camera before we sign off. focusing on the wires, thanks. Good cat. Yeah, that... I kind of agree with you, Starlight, the separate and opto-isolate. I think that might be more effective than just throwing capacitors at the solution. So yeah, I mean, I might try to see if I can dig up an opto-isolator that would work for this. Because especially given that now it's just one control signal, I mean, I need something that's moderately fast because I'm trying to do these like 1 or 2 microsecond pulses, but I mean, I'm pretty sure I can find an opto-isolator that's happy with... I mean, that's a little high for an opto-isolator. Aren't opto-isolators often only good up into the like a few hundreds of kilohertz? That might take some careful design, but I'm pretty sure we can do it. It's also tempting to AC couple the PWM signal so I don't have to worry about the ground bounce so much. Is that a terrible idea? Part of me thinks it's a terrible idea to AC couple the PWM signal, and part of me thinks it's great. Because like typically what I'm doing here is it's ground almost all of the time, and then I occasionally feed in these, you know, pulses that range from like a couple microseconds to maybe, I don't know, whatever the maximum duty cycle I feel like using is. No attempts at like rate limiting any of these edges except for my cheesy series resistors, which I was even under the assumption earlier that those were higher value, because like I was looking at this earlier and I thought, oh, those 100K resistors, those are the ones I added, but I was looking at the chip upside down and I think they're like 3.3K or 33K. I saw the double oranges, but I forget what the multiplier was. The rest, like the video switcher, is already isolated. That is true. That yeah, at least some of that was definitely radiated. Otherwise, it wouldn't have been messing with the video switchers, right? So yeah, I mean, some of that might still be coming from the motor brushes. So I was also thinking about maybe putting like a small disc capacitor right across the motor. That might just help with the commutation noise. Gosh, brushed motors are just no good, right? They're just throwing noise everywhere. I mean, this thing was designed for electric scooters, not video studios, right? But we can get to the bottom of this eventually. Power the motor separately for checking the motor brush noise. Yeah, definitely. Yeah, I mean, I would definitely do that. I think it would just require cutting some of those wires because I didn't add connectors, but it would be a thing to do. Capacitively couple everything. Pretty surprising that so much noise was just coming out of this power supply. I mean, I probably should have checked that, but it was interesting that I wasn't seeing that all the time. It seemed to show up somewhat abruptly. So I don't know if this might have like a bad solder joint on the capacitor somewhere. This is the beefy boy that we were powering this off of, rated at 13.8 volts at 30 amps. All right, well, thanks so much for joining me on the stream today. Let me know what you think. Let me know if you have requests or scheduling or topic feedback or any of that. I'm all ears. If not, I will just keep trying to do these. I've been failing to do them frequently, mostly just because I've been having trouble personally with all of this, but I feel like there aren't that many reasons for me not to just stream like every day. It mostly just comes down to like body and brain need to be in the right working state. So I'm trying to work on that. But um, yeah, let me know if you have thoughts about like scheduling and topics and anything else. And as always, big thanks to my patrons. The folks at Patreon supporting me are really making this possible. I don't have other sources of income beyond like Patreon and the couple bucks I get for Fade Candy still. So, like, I could try to get another tech job and not be super burned out at that, but this is really the thing that's sustaining me at trying to do this video project still. So it's important to me that, I know what my patrons want and that I can try to make some content that seems meaningful. So certainly give me any feedback if you have any of that. If not, I'll see you soon. 13.8 is also kind of common for like automotive stuff. Yeah, I don't know if this was designed as a battery charger supply. I think it was designed for something automotive adjacent. But yeah, I mean, it seems like the kind of thing that you would get for a ham rig, and it seems like this noise would be really bad for ham radios, but then maybe the radios already have like giant filters on them. But yeah. Alright, see you next time.
You are currently the only person in this conference.